Good morning, ladies and gentlemen. Thank you for staying here. On behalf of the Vice-Rectorate of Research and Transfer, it's my honor to welcome you to the Polytechnic School of Universidad Carlos III de Madrid for the second International Conference on Advanced Materials and Energy Storage. This prestigious event, like the first edition, brings together leading international and national researchers dedicated to advancing this critical field of study. One of the strategic pillars of Universidad Carlos III de Madrid is to foster research that is excellent, international, and interdisciplinarity. In this regard, the success of this conference exemplifies our commitment to these goals. I would like to extend my sincere congratulations to Professor Bareth and Dr. Pandit for their exceptional efforts in organizing this event. Their collaboration, facilitated through the Marie Curie Connects Plus Fellowship Program, serves as a model of international cooperation in high-impact research. This initiative showcases how global partnerships can drive forward cutting-edge scientific achievement and ensure the effective dissemination of knowledge through platforms such as this conference. I would also like to commend the Material Science Synthesis and Processing Research Group and the Department of Material Science and Engineering and Chemical Engineering for their outstanding works in organizing this event. Their dedication has been pivotal in assembling an impressive lineup of contributions and speakers, which I'm confident will inspire productive discussion and collaborations. I trust that you will find the scientific program stimulating and enriching throughout the day. Moreover, I hope you have the opportunity to explore Madrid and enjoy its vibrant social and cultural offerings during your stay. So thank you very much, and once again, welcome to Universidad Carlos III de Madrid. Thank you. Dr. Pandit, please.
Hello. Yeah. So good morning, everyone, and to my distinguished speakers, honorable speakers, my colleagues, researchers, all are welcome. As a conference chairman, it's my honor to welcome you all in the second International Conference in Advanced Materials and Energy Storage 2025, here hosted in University Carlos III de Madrid. On behalf of SIGMAT Research Group, associated with Material Science and Engineering and Chemical Engineering, and on behalf of organizing committee, I extend my warmest greetings to all of you. First and foremost, I want to thank our sponsor, Biologic, whose support throughout this conference are instrumental. So thank you for that. I also extend the gratitude to all the participants and contributors who come from all the corners from other countries, and they came here in Madrid and make this event as a great success. So the field advanced materials and energy storage is a forefront for nowadays, because we are facing some environmental issues related to energy storage and things. So we need some cutting edge technologies, and this conference is all about it. We made it last year, the first international conference, and it was a huge success. So we are continuing in the second term, and hopefully we'll do in the third term, fourth term, and it will continue, because this issue is very important in our society, in the world, and for all of us. So over the next 2 days, we'll explore some groundbreaking research and on the topics of lithium-ion batteries, sodium-ion batteries, all the battery aspects, energy storage, electrochemistry, supercapacitor, fuel cells, all the energy-related aspects. So I encourage all of you to engage actively in all the sessions, because all speakers are very expert in this energy storage and advanced materials field. So I think all of you get some fruitful insight in your research, and it will help you in your research and career and everything, okay? So with that, it's my great pleasure to declare the second international conference on advanced materials and energy storage 2025 officially open. And thank you, and I wish all of you thank you for supporting us, and let's make this conference a big success. Thank you all.
Okay, well, so good morning, dear guests. We will start the presentations with our guest, Dorothy B. Ravensbach, who is a professor in materials chemistry at the R House at the university. She obtained her PhD in nanotechnology in 2011 before moving on to postdoc position at Massachusetts at the MIT in the group of Professor Jetming Chang. In 2015, she joined the University of Southern Denmark and established her own research group. In 2021, she moved on to a full professorship at Aarhus University, where she heads a research group of more than 15 members and is soon to be leader of a new research center for sustainable energy materials. And during the past over 10 years, her research has focused on developing new electrodes for ion batteries and elucidating structure property relations for battery materials.
Thank you very much, and first of all, thank you for the kind invitation to come here today and tell you about our work. And I will focus on our work with Operando studies, so structural studies of battery materials. But first, just a brief intro to me and Aarhus University. So we are positioned here, almost in the middle of Denmark. And this is the university campus near the city. So it's a very nice place, both for students and employees. And this is my group as it looks now, and we focus mainly on battery materials. So we do a lot of synthesis. Most of us are chemists and crystallographers. We do electrochemistry, of course, and then we focus mainly on structural studies, both on multiple length scales, so ranging all the way from doing tomography on the millimeter scale and down to the angstrom scale, doing crystallography and scattering studies. The work I will tell you about today is mainly done by Maria here in the nice hearted jacket, and Morten and Andreas, who now left my group, but I thought I would highlight them anyway. Also, it helps the gender balance a little bit. You see, we are a very female-heavy group. So I reckon that most of you know that in a battery we have two electrodes, and the concept is that these electrodes are able to deliver and receive electrons, and at the same time to keep charge balance, they are able to accommodate intercalation or deintercalation of the active ions, here lithium ions in a lithium-ion battery. And these processes, they induce some interesting phenomena in the electrodes. So they oxidize or reduce species in the host structure. So if you have a transition metal oxide, the transition metals are reduced or oxidized. And this causes a change in the radius of that metal or that species, and that can drive a phase transition. Also, we have intercalation and deintercalation of the ions, so the structure also needs to accommodate the ion. It takes up some space, it causes some repulsion or minimized repulsion, and therefore that also induces a phase transition. And these phase transitions, they can be of a pure structural nature, so we just have a change in the structure. Of course, if we have a conversion type material, it can also induce a chemical reaction. But the materials that I will focus on today, we are looking at the structural phase transitions. And understanding these transitions, it's very important for the battery properties because they govern the thermodynamics, so that's the potential of the battery. They govern the kinetics, so that's the power, how fast can we charge and discharge the battery. They also govern how reversible is this transition, so how good can the battery keep its capacity while we charge and discharge many times. And also we may have side reactions which can of course hamper the reversibility, but it can also cause safety issues if for example, we have oxygen evolution. So what I will tell you about today is first how we study these phase transitions using X-ray methods. Then I will tell you about 2 cases of sodium-ion battery electrode materials. And then I will finally, on my very last slide, give a little bit of perspectives on what I think will sort of happen as we move forward in the regime of operando methods. So what we mostly use for our operando studies is a cell like this, so either an Ampeg cell or a Danois cell, that's just some abbreviations, just the name of the cell. And in these cells, the principle is that in the middle here, we have a cavity for our battery stack. So we can put our electrode of interest, of course a separator, an electrolyte, and a metal anode. And typically, to get the best signal, we make the electrode as freestanding pellets, which we put into this stack. And then the stack is encased between glassy carbon windows. And this has several advantages. So first of all, glassy carbon is a rigid material, so we get a good stack pressure. Also, they are conductive, so we also get good contact on each side of our battery stack. And finally, carbon is a relatively low set material, so it means that we can shine an X-ray beam through the cell and collect the scattered or the absorbed signal on the other side. So we place this cell typically in a synchrotron X-ray beam. We use several different synchrotrons. Then we cycle it, so we get the electrochemical signal, and we then do repeated data collection at a certain frequency, say every 5 seconds or 10 seconds, we take a picture or we take a scan. And then we can do this in 3 sort of modes. So we can, of course, do diffraction. That's, I would say, almost the simplest we can do, where we get the changes in the crystalline structure and can follow this. We can also do a total scattering experiment, so we can do PDF analysis, and I will get back to what this is, where we can probe changes in the local structure. And finally, we can also do absorption spectroscopy, so we can get elemental specific information about the oxidation state and the local structure and the material. And it's really an advantage that we can do this on the same cell, so we have exactly the same conditions. And we can even do these 2 at the same time or these 2 at the same time. So just a brief slide on PDF analysis. So PDF stands for pair distribution function analysis. And when we collect a PDF, we basically do a normal diffraction experiment. The only difference is 2 differences. So one is that we collect data to a very high scattering angle. So high that you would say, oh, there's nothing. But it's really important to have the contributions at very high angles. And of course, we also need pretty good quality, so we cannot, the time resolution suffers a bit. Then we take this data and we do different mathematical corrections for the background and for the amount of scatterers and so on. Then we do a Fourier transform that brings us from the reciprocal space into the real space. And what we get here is the PDF. And basically the PDF is just a histogram of all the interatomic distances in the material. So if we have two atoms a certain distance away, we will get a peak here. So these are bonding distances, you can say. If we have a monoatomic material, then the integral of the peak will also equal the coordination number. But you know, we rarely have monoatomic species in a battery, so that's not the case. So what we can do is that if we have a crystalline structural model, we can calculate a PDF. And that allows us to do a least square refinement. So if you know a Rydberg refinement, we can refine how does our structure look. If we have a crystalline material, we will see well-defined peaks or correlations up to quite high bonding distances, because the distances with the long-range order are the same throughout the material, right? But if we have something with a lower degree of crystallinity, say a nanoparticle or something partly amorphous, then we will get well-defined correlations to a shorter length here. So the correlation length is different. But we can still use a crystalline structural model as our starting guess for the refinement. We just also refine this coherence length. So we get, you can say, sort of the crystalline size, and then we get information about how does the average motif in the material look. So these are just images of how it looks at the synchrotron, and as you can see, we typically cycle 6 or maybe 8 cells at the time. So we shoot on one cell, and then we move the stage, so we shoot on the next one and the next one and so on, because quite often the batteries are cycled so slowly, maybe one discharge in 5 hours or 10 hours, that we can easily sample from more than one battery at the time. So just a small note here that when we do this, we usually move the beam spot every time we come back to the same cell. We call this battery bonanza. And this is because we have discovered that, especially at lower energies, we can have quite severe beam damage at the synchrotrons. And what happens when we have beam damage? Actually, beam damage is a bad word for this phenomena because it simply just hinders the electrochemical reaction from happening at the spot where the X-rays hit. So it means where we are probing, we don't see any reaction, but at the rest of the electrode, the reaction is going on as it should. If we then move the beam to another spot, then the reaction will start happening. So it simply hampers, and the origin of this is still not known. It's something that we are looking into, but if you go to a synchrotron for these kind of experiments, it's something you should really look out for. It cost me maybe 1.5 years of ruined data that I hadn't discovered this. We can also do experiments in our home lab, both PXRD and also absorption spectroscopy. Of course, the quality is not as good as it is at the synchrotron, but it's decent, and we can screen materials. So now let me move on to the cases, and I want to talk about sodium-ion batteries. And a lot of you probably are quite familiar with the topic. And the idea is, of course, that we make a battery that in many ways is similar to the lithium-ion battery. Sodium and lithium are in many ways behaving the same, so we can use much of the same know-how. Still, the materials, or the sodium and the lithium, are so different that we do have to reinvent many of the things in the battery. So it's not as easy as it may sound. And that means that the materials for the electrodes has to be developed again, you can say. And the motivation for this is, of course, that sodium is much more abundant than lithium. So the price is much lower. and the sustainability is much higher. So the materials that I will talk about today all fall in the class of layered transition metal oxides. So they are in many ways similar to the materials that we have in, say, our electric vehicles today, where we have these NMC or NCA type materials, where we have a transition metal in blue here, then we have oxygen in red, and then in the lithium-ion battery, this would be lithium, but here it's sodium. And these materials, they can be synthesized in two polymorphs. So we have an O-type and a P-type. And this refers to the environment around oxygen. So the O-type has an octahedral coordination around sodium, and the P-type has a prismatic coordination around sodium. And this is, in a sense, all good. But what then comes as a bit of a trouble is that we can quite easily, during intercalation and deintercalation, have sliding of the transition metal oxide layers. So the blue layers, they glide relative to each other. So for instance, we can go from an O to a P or a P to an O. And these transitions can cause irreversible behavior. So we need to understand these, and also they are structurally, they're quite challenging to dig into. So first, I will show you a case where, as we cycle the battery, we induce disorder in the material, and that causes sort of electrochemical death. The material dies. And the material is a O-type sodium chromium oxide. And it's been known for a while that if you cycle below, say, 3.8, then you get maybe not a fully reversible behavior, but you can cycle the battery, as we see from the CV curve here. But if you go higher up in voltage, then you lose all capacity. So we did the Operando experiment. So here we have the scattering angle, and then we see the Bragg reflections. So the more red they are, the higher intensity they have. And if we only cycle to this 3.65 here, we see that we have a crystalline material, we have several phase transitions, but we come back again to the same starting point, and it's fairly reversible. There's some very interesting behavior here, but I will not go into this. Instead, I will focus on this sample here, where we took it all the way up to 4 volt. And as you see, then we lose most of the diffracted intensity. So the material becomes not amorphous, but it has a very low crystallinity. And it had not been known what actually happens up here. So we took a sample to this point, and then took it out of the battery, collected the diffraction data first, and we saw that we couldn't analyze this. So instead, we looked at the pair distribution functions. And by screening a lot of structures, first of all, we could rule out that we had formation of a rock salt, which was otherwise commonly believed. But we could also see that what we in fact have is a highly disordered O3-like material. And it has quite short coherence length, so it means that the order is on the scale of about 5 nanometer. The data also suggested that chromium had migrated from the blue layers here and down into the sodium layers, and then occupying a tetrahedral position. But that's quite hard to prove from these data. So instead, we went to a beamline where we could collect the absorption spectra. And here, if we compare with different reference materials, we can clearly see that we have chromium sitting in a tetrahedral position. And what happens is that as we have chromium 4, as we oxidize the cathode, then it disproportionates into chromium 3 and chromium 6. And chromium 6 is, of course, very small, so that can easily migrate in the structure, and it really wants to be in a tetrahedral position, right? So that moves down to the tetrahedral position. And the fact that we have these here, of course, causes a contraction of the layers or the surrounding around this tetrahedral, because it shields the repulsion between the oxygen. So here we have a contraction, but it doesn't happen throughout the structure because it's not everywhere that we find a chromium in a tetrahedral position. So this induces the disorder in the material. And another thing that it also does is that it blocks sodium from re-entering the layers. Of course, it does so because it's sitting there, but to maybe a more pronounced extent, it does so because the layer contracts, and that hampers sodium from re-entering. Yes, and I just want to mention that, of course, we can also look at this PDF under operando conditions, and when we do so, we actually prove that this disordered phase, it forms as a two-phase reaction, and as it nucleates, the chromium is actually already on the tetrahedral position. So it is really a new disordered phase that nucleates. It doesn't form as a solid solution. So the second example that I brought is a case where we have, again, disorder as we charge and discharge, but now it is reversible. So we come back to a crystalline state, and the battery survives very well. And this is a study, you can say, in a big cohort of materials, where we wanted to look at layered materials solely based on iron and manganese. And then we wanted systematically to see, okay, what happens if we put in other types of materials. So we can synthesize the P and the O, and we can also synthesize hybrid, and then we can vary the ratio between iron and manganese, and we can dope with other materials as well. So I mainly want to talk about, or I only want to talk about O3 actually, and I want to stay with the mother material. If we look at the capacity, it's not so high, but it's decent for a sodium material, and actually it's more stable than we thought, so it's undermining our reasoning a little bit, but that's good. And what we see is that when we synthesize the material, we always have a little bit less sodium than 1. And this is because manganese is not fully reduced in the as prepared state. So we get a little bit less sodium than 1. And that actually, it doesn't really depend on what we do. We always get this. And this is, of course, a shame, because that will lower the capacity of a real full cell battery. So we will have to solve this somehow at some point. So if we start with this O3 material and we look what happens as we start extracting the sodium ions, then first we will have formation of a P-type material, and then we will have formation of what was typically referred to in the literature as an OP material. So it means we have an O layer, then a P layer, an O layer, a P layer, and so on. As we discharge again, we get another OP structure, and then we come back to O. And as we then fill it up completely with sodium on the discharge, we get another Jahn-Teller distorted phase here, which is also very interesting. But I want to focus on the high charge phases today. So these two OP phases, they have been described in the literature, but actually when you look at them, you will discover that you cannot really analyze the data based on these models. So the unit cell fits, but the atomic positions are wrong. So to look further into this, we went for the program FALTS, which is actually developed here in Spain by Monte Casas Cabanas. And this is a program used for treating stacking faults. So we can understand the gliding of these layers. And here we start defining first a layer where we have the sodium layer and the transition metal oxide layer. And then we define a stacking vector, so one that brings us from an O layer to an O layer, one from an O to a P, from a P to a P, and from a P to an O. So it's kind of like building with Lego bricks and stacking them differently according to each other and describing this with vectors. It's a very fun way to work with structures. It's also challenging when you are a crystallographer because you have to let go of symmetry, which is not so easy, but it's really fun. Also, we refine different parameters. So we get the ratio of O to P layers. We also get the probability of having these different transitions. So basically the probability that if you are in one type of layer, what are the chances that the layer type will be different in the next type? And we get the thickness and the sodium occupancy and so on. And we can use this model to refine all our data. And for the O starting phase and the P that forms right after it, we see that we have almost 100% O layer. We have a little bit O layer in the P, so a little bit of stacking faults, but not a lot. But then as we move to these OP phases, we see that we do have around 50% O-type existence. So that fits with having these crystalline OP structures where we have O and P and O and P and so on. But then when we look at the probability of going from O to O or P to P, we see that that's about 30%. So that means that in 30% of the cases, it will stay in the same layer type. The next layer will be of the same type. So we will therefore get some domains, as illustrated here, where we have O domains and P-type domains. So that, of course, does not give us a crystalline material, right? Because then it would have to alternate in a regular manner. We also studied this with the absorption spectroscopy. And I could say a lot about this, but I will not. So I will mainly focus on the ion pre-edge here. And this pre-edge, even though it's just a little signal here, that's actually the most interesting part, because if we see no pre-edge, it means that iron sits in a symmetrical environment, like a perfect octahedral. If we have distortion, so that could be Jahn-Teller distortion, it could be iron moving to a tetrahedral, it could also be anionic redox. Then we will see the edge coming up, or the peak coming up. So if we integrate the intensity, we see this behavior first during charge and discharge. And we can now couple this with the information we have from X-ray diffraction and also from cyclic voltammetry. And we can see that we first have a manganese active region down here where we have a little bit synergistic effects on the iron. Then we have here we have iron 3 going to iron 4, and here we see Jahn-Teller distortion of the iron 4, but we probably also, or we might also see a little bit migration into a tetrahedral position, but if we do, it's relatively reversible. And then finally up here, where we during the first cycle have this big peak that doesn't reappear upon the second cycle, we believe that it's mainly anionic redox. And anionic redox can occur in different ways. So we can have release of oxygen. We could have formation of OO dimers or O minus species. And we don't know exactly what's happening yet. And what we are now looking into is doing absorption spectroscopy on the oxygen edge to probe what's actually happening. But it's very challenging experiments. There is oxygen in everything, basically, and also the samples have to be very thin to get the right absorption. Good. So let me now get to the second cycle of this material, because you see, if we first charge and we get these OP phases, then as we discharge again, we come down here, it goes well, and then on the second cycle we have formation of X. And it has been known as X for a long time. This is what we call something we don't know what is, right? And then as we cycle repeatedly, we all the time get now this X. We never get P or OP again, we just get this X phase. So to analyze this, we went again to our false model. And what we now see is we still have about little more O, but still around 50-50 O and P in this phase. But we see here a dramatic difference in the PP stacking or OO stacking. So it means that if we are in an O, there is a much higher chance now that it will stay in an O, and the same for P. So now we will get much larger domains of O and P type structure. And if we look at the behavior of what's going on, we can see that if we look at the A-axis, we have a linear decrease. So that means that most likely our transition metal is being oxidized as we expect, because that sort of determines the size of the AB plane. We also see that around 3.4, the O to P transition stops. And then one interesting thing is that we always see a higher sodium occupancy in the P layer. So it kind of looks like that the P-type material is about to nucleate, but then something hampers it from forming fully. And therefore, we just have these large domains of O and P. And what could hamper this is if we have just a little bit of iron that have migrated into the tetrahedral position in the O-type layers, then that will actually prevent it from gliding into a P-type layer, because between the prisms in the P layers, there are no tetrahedra. So it cannot do this if the tetrahedra is occupied. But we don't know this yet, and we will have to investigate this further. So I have no idea how I'm doing on time, but I will offer you a little bit perspectives on Operando battery studies as my final slide here. So I think that more multimodal options will emerge, like here where we do the diffraction while we also do the absorption spectroscopy. And this is extremely useful for batteries, at least, because if you have worked with batteries, you know that it's very hard to ensure that you at a certain point in time or a certain voltage point are at the exact same state of charge, because it depends so much on small variations in the resistance in the cell and so on. So having more information from one cell is really good. I also think that with the sort of technological advances that happens both in X-ray sources on in-house instruments and maybe mostly on X-ray detectors, it will also be increasingly possible to do quite good operando experiments at home. And I will say the setup that we have built in Aarhus for this is really working nicely, and we easily get results that we can will refine and publish. Synchrotrons, as you may know, are increasing the flux for good or bad. But on the good side, it means that the time resolution will increase. So we can begin to think about doing fast experiments to really study systems where we push the kinetics, which I think is really interesting, and maybe especially if you are in the supercapacitor business. Yeah, I just said this. Also, it will give us new options for operando mapping and imaging. But on the bad side with this flux is that beam damage becomes an increasing issue. So it's something we have to look out for, and it's also something we have to learn how to mitigate, to study these systems in a good manner. And with this, I just want to thank everybody on this slide and you for listening to me.
Hello. Hi. So thank you very much for your wonderful presentation, Dorothy. Does anyone have any questions regarding our topic?
Hi, thank you for that presentation. It was actually very intriguing to me. My question is regarding the inoperando studies of batteries. Are you familiar with any types of studies like the PDF studies with solid-state batteries, where you see multiple layers of different phases, and what are some of the complications with these known types of studies?
Yeah. So Operando studies of solid-state batteries are out there and increasingly emerging. I think now people are beginning to have built good cells that also gives fixed like the stack pressure and everything. It's a little bit more involved to build such a cell, right? For if you particularly focus on the PDF studies, they become quite complicated because in a PDF you see everything. First of all, not just the crystalline, you see also all the amorphous. And because in reciprocal space, we have the big advantage that we have the separation in d-spacing, which makes it quite easy often to distinguish different phases from each other. But in PDF, everything is collapsed, you can say, down to a quite narrow range of interatomic distances. Also because the materials that we're working with essentially are quite similar, right? If it's ceramics, oxides, and that. So you could have a very hard time distinguishing the phase behavior from each other. What one could think about doing is making very careful reference measurements so that you would be able to actually subtract signals from different components in your cell that you're not interested in. That can be done more effectively in the direct space than in reciprocal space, so that's an option. But it's a big challenge.
Yeah, thank you very much.
Do we have any other quick question? Sorry, I will come to you later.
Hi, thank you very much for an excellent talk. I have many questions, but I'll ask one. Just on the last point, in terms of degradation, for how long can you measure in one spot before you have to move to the next one, especially at low energies?
Yeah, that's a very good question. Which I don't have a very good answer for.
I guess it depends on the material, but...
Yeah, so usually so actually what we have started now even doing is that when we expose one spot, when we do measurements at low energies, we even sort of wiggle it to spread it even more. But so far from what we have seen, if we do, say, a 5-minute exposure at Balder at max 4, which has a quite high flux, we are okay if we then wait, say, for a couple of hours coming back to the same spot. But I don't have a very good scientific qualified answer yet.
No, I just wanted to know roughly like the time is.
But I think what you should do is that you should make like a test and expose a spot, and then do like a line scan across afterwards, just to see do you have a difference in the phases in the spot and outside the spot.
Thank you very much.
Thank you for this presentation, didactic presentation. I have two questions rapidly. I am not skilled in inorganic materials, but my first question is related to the technique. What kind of electrolyte can be used in this operando analysis? And second one deals with the possibility of sodium-ion battery to be used, for example, in electric cars.
Yeah. So in terms of the electrolyte, we haven't seen any limitations to that. So we typically use the standard commercial electrolytes, but for some studies we have used more specialized ones. We have also done a lot on magnesium-ion batteries, and we use the electrolyte that works best for the electrochemistry, and we don't see any difference really. And in regards to the sodium-ion batteries, so the best performing sodium-ion batteries, they are on the level of the lithium iron phosphate LFP type batteries, which you will find in the small battery pack of the Tesla. So it's definitely possible, and in China they are already producing cars with sodium-ion batteries. But of course, they come with a shorter driving range than NMC, but for a city car.
Okay, so thank you once again, Professor Ravensbach. Let us move to the next guest. He is Angel Larrea. He obtained his PhD in nuclear physics and particle physics, working on X-ray detectors using superconducting materials. After his postdoc at the CNRS in France, he joined the CSIC in Zaragoza in Spain. And he has worked on high-temperature superconductors, directionally solidified ceramic eutectics, ancient materials, and solid oxide cells, trying to understand the relationships between the microstructure and the physical properties of the materials. In recent years, he has led several industrial projects for the development of new lead battery technologies. And he has been a member of the Commission of the National Evaluation and Foresight Agency of the Spanish government. So, do you... No, we can take it. No, of course.
Es el punto. No, eso es para pasar. Si no, usar el dedo. Don't worry. So, sorry for the delay. Thank you very much. First, I would like to thank the organizers for inviting me to this nice workshop. I'm very happy to be here. Yes, I have to. Okay, thank you. Sorry. Yes, I'm not used to be here. Okay, thank you. So this work is. I'm going to focus more in the techniques of operando studies in batteries using neutron scattering, that mainly that in the batteries, and this part of a work that has been done in collaboration between us, the Instituto de Nanociencia y Materiales de Aragón, The Excite company, Excite Technologies, is a large manufacturing company of lead cells, and the National Institute of Standards and Technology in USA. And for the particular experiments, we have also collaborated with the with Oak Ridge National Laboratory and with the Pulsar Institute in Switzerland. Well, the idea is we would like to analyze by neutron scattering the charge-discharge processes in real battery electrodes in operando condition. What we mean by real batteries electrodes? That means they are industrial batteries that are electrodes that are manufactured in the company, and they are the same that you can find in your car or in your UPS. That means that we have a thick electrode. For the minimum cell we can make with lead battery, we have about 1 centimeter of the cell, so it's 10 millimeters. This is why we are forced to use neutrons to obtain information in operando conditions from inside this kind of batteries. So I have put here for comparison the scattering cross section for X-ray for the common element you can find in a lead battery is hydrogen, oxygen, sulfur, and lead. For lead, we have only represented 1/4 of the cross section because the interaction with X-rays with lead is huge. And in comparison, in green, I show you the the cross section for thermal neutrons. You can observe as the comparison of lead is, they have no comparison. The interaction of neutrons with matter is very strong, but is short range. And it interacts only with the nucleus, so the interaction is very weak. So neutrons has a very high capacity of penetration in the matter, and particularly in comparison with X-rays in heavy atoms. For instance, I present you in this, in the second graph, the event transmission in lead dioxide. Even if we use high energy X-rays, the penetration is no longer than 2 or 3 millimeters. But using cold or thermal neutrons, we can penetrate several millimeters, even 1 centimeter. So this is because the interaction is different, and the information we are going to obtain by neutron scattering is complementary to that information we can obtain with X-rays. So this is why we have selected neutron, because we think that for this kind of batteries, X-ray is not possible to obtain information from inside. Well, as you know, the lead batteries is not a new technology. They were invented by this guy, Gaston Planté, long time ago, based in previous work of these two NAS guys. But this is a technology that is still in the market. Most of you in your car have a lead battery, and also you can find lead batteries. For instance, this is the new generation of the Spanish submarine. The batteries for this submarine are lead batteries that are made in the Zaragoza plant of Excite. And in fact, there is in European Union and USA, there are more than 70,000 people working in direct manufacturing of lead batteries. 10,000 of them in Spain. We export about 70% of the Spanish production, and there a plant of Excite in Zaragoza, in our city. This is why we collaborate. We have a close collaboration with that company, with 400 people working there in direct manufacturing. And also, almost 100% of the lead of the batteries is recycled. So we are in a circular economy. The principle of operation is in this slide, in this part of the slide. In charge style, we have two nanostructured porous electrodes. The positive is made by lead dioxide and is impregnated by sulfuric acid. Sorry. And the negative electrode is made by metallic lead and also is impregnated by the sulfuric acid that acts as an electrolyte. So during the discharge, you have there the reaction. Mainly, the transformation is from lead or lead dioxide to lead sulfate. In that product, in that chemical reaction, you can obtain about 2 volts per cell. And for the charging reaction, you have the opposite reaction, that when from the lead sulfate, you recover the lead dioxide and lead. So this is very well known. And we have used 2 neutron scattering techniques. The first one is more experimental. I'm going to try to describe the steps we are in the way to develop this technique for operando studies of batteries. This is the quantitative wavelength selecting neutron imaging with Bragg edge analysis. The experiment was first designed for NIST, for USA, but they had a problem with this, with his reactor, and we were forced to move our experiments to the Polscher Institute in Switzerland. And the second one that is more well-known and more established is the gauge volume neutron diffraction. And we carried out some experiments in the Oak Ridge National Laboratory. So I'm going to try to describe the first technique. The theoretical basis is in that part of the slide. We have a neutron beam that is interacting with a crystalline powder, and one of the possible interactions you can have there is Bragg diffraction. But for to have Bragg diffraction, there is a condition that the wavelength of the particle has to be lower than this in red 2 times the interplanar spacing. So this is called a Bragg edge. So if the wavelength is higher than this threshold, there is no possibility of Bragg diffraction. So if we represent the cross-section, for instance, for copper or iron, if the wavelength increase and is over this Bragg edge, there is a sudden decrease. That is called as a Bragg edge. So how we can use this technique to image the crystallographic, the concentration of some crystallographic phase. So we can compare the image of the material just before and just after a Bragg edge. So in the areas of the image where the intensity of the transmitted intensity is similar, that means that we have no contrast and we have no that phase. In the areas where we have a sudden variation of the intensity of the image in a particular pixel, that means that we have that particular phase there. We have applied this to the positive active mass of a lead battery in different state of charge, and you can see there in the left part the transmission pattern for lead dioxide in black, and in red the transmission pattern of lead sulfate. You can observe that the patterns are totally different, and this very big Bragg diffraction there at about 3.4 Armstrong is due to the presence of the is by diffraction of the 211 crystalline plane of beta PbO2. This is no longer present in a discharge positive active mass, but you can observe there a Bragg edge that is produced by diffraction of several lines of lead sulfate. So the idea is to use this difference to image the presence of these 2 phases, and here you have an image of the 3 containers that contain powder in 3 different states of charge, and we can use this pair of wavelengths. The blue ones are for lead dioxide, and the red one for the lead sulfate, to compare and to locate where these particular crystalline phases are. And I don't know, you can see that in red we have represented the pixel where we observe a high contrast when we change the wavelength from lambda 3 to lambda 4, and in blue, the places that show contrast when we change the wavelength from lambda 1 to lambda 2. So we can map in a quantitative manner the concentration of a crystalline phase. So we only need 2 different wavelengths for each crystalline phase. The idea is of the experiments is a neutron incident beam, the sample that in the ideal case is an operando cell, and we can make this analysis pixel by pixel. This is the first approximation of the concentration of a crystalline phase. We have made several experiments in Pulsar Institute. For a single material container to characterize very well the transmission of each component, for plates, also for operando cells. We are now analyzing and trying to reduce the noise. One of the main issues we had that when we need to move from NIS to PSI, the beam intensity in PSI is 130 times lower than in NIS, so we have a problem with dealing the noise. Here, for instance, you have an image of a positive discharge plate, and this is the field of view in our experiments, and we selected these yellow rectangles to avoid the contribution from the LED bar of the grids. And you see here the transmission curve as a function of wavelength. There is no Bragg edge due to the LED, metallic LED. There is a small Bragg edge due to the lead dioxide, and there are larger Bragg edges due to the presence of lead sulfate. And this technique is quantitative. If we measure the beam attenuation, we can get the quantitative concentration per pixel. So I show you in red the concentration we obtain with the first approximation of these techniques, and in black, the concentration we should obtain from neutron diffraction, from conventional powder diffraction. I can show you that the agreement is very good and is very encouraging. The next step is to do that for operando cells. Then we have more electrons, and we have the sulfuric acid that is dispersing the neutron. So we are now analyzing this data. I prefer not to present for the moment the quantitative result, but the idea is to get a map of how the phases are evolving during the charge and discharge. To encourage us, I used to show this image is the first broadcast TV picture that was emitted in long time ago. You can compare that kind of image with the image you can get in your home TV. So the difference is noise. I had copied this idea from Albert Tarancon that used that also for solid oxide fuel cells. I can inform you that this is the image of a lady. So we are now working in reducing the acquisition time and reducing the noise. And the other technique is more conventional, is the operando case volume neutron diffraction. The idea is this experiment was carried out in Vulcan instrument of Oak Ridge National Laboratory. The idea is we have an incident neutron beam, and with 2 slits, we select a small beam. Small for neutrons means 1 millimeters or some millimeters. And with the colorimeter, we can select a volume element, a voxel, from which we obtain the neutron diffraction, conventional powder diffraction. For instance, this is a powder diffraction from a single voxel with 2 minutes of acquisition. We can analyze this. This is a time-of-flight spectrometer, but we can do conventional analysis and to obtain the concentration. So we apply these techniques for open circuit static maps to get more, with more acquisition time to have more accuracy, or for dynamic operando maps when we reduce the acquisition time Bueno, no te preocupes, estoy acabando. Yes. I will still continue using my finger. So, for instance, this is the accumulated diffractograms for the whole area analyzed. We have obtained some information we have discussed with the lead battery community. So the difference is that for this information, of course, as you have explained, it's not necessary to stop the cell, to break down, to get the crystalline phases to wash. So there are some crystalline evolutions of this. For that, they always claim that even in the charged new battery, you can find lead sulfide. We have shown that no, this lead sulfide is produced after when you stop the operation and you wash the material. So these are, for instance, concentration maps, also in open circuit of the three electrochemically active phases, alpha and beta PbO2 and lead sulfide. You can observe that after discharging is mainly the beta, the active phase, as is well known, and we have produced lead sulfide. And you can observe that there is a vertical gradient. There are more lead sulfide in the bottom part. This is by some type of gravimetric effect in the electrolyte. So this is called stratification in this field. We can also characterize the discharge rate. We have used in these experiments the internal grid, lead grid from the current collector as internal monitor for calibration. So as we know the amount of lead, we can use this element for calibration, and we can obtain the concentration of every element, not only in a relative manner, also in an absolute manner. So we can obtain, for instance, the mass utilization, the percentage of the active mass that has evolved during a discharging, and also to compare this amount with the amount of electricity we have provided, and to compare these two quantities using the Faraday constant, for instance. Because the efficiency of this kind of batteries, mainly during the first step of formation that is done in the company, is one of the most important contribution to the final price of this kind of electrochemical devices. And yes, last one. This is, for instance, how we carry out a dynamic map. It's, of course, accelerated. Each voxel is acquired for half a minute, so we can show where the intensity of voltage of the cell is evolving, how the crystallographic concentration is also evolving. And as a final conclusion, with the wavelength selective imaging, we have still to work because it's a new technique to get a result, but this technique is also possible to be applied with no problem with lead battery. And well, that's all. Thank you. Thank you for your attention.
Okay, so Angel, once again, thanks you for your presentation. We're running a bit tight on time, so let's keep it to just one question, and maybe then in the coffee break, if anyone else has a doubt. So, anyone would like to make some question?
Hi, thank you very much for the nice talk. You said that the neutrons were very good when you have large samples.
Yeah.
Do they have any restrictions when you have small samples?
Well, the restriction is that the interaction is weak. So if you have a very small sample, you will have to acquire for a longer time. So, of course, penetration and spatial resolution and time resolution are opposite. So if you are interested in a small sample with good spatial resolution, it's better to use X-rays.
So can you give some numbers, like?
Sorry?
Can you give some numbers, like minimum amount of sample or
no. I have not made calculation, but these experiments are thought for electrodes that have 3.4 millimeters in thickness. The porosity is about 50%, so we are thinking in about 1 millimeter. So if the electrode is 200 microns as he has present, I think, I don't know, but of course you have to count for more time. Here, the spatial resolution is about 1 millimeter. So if you are interested in a spatial resolution of 50 microns, probably you have to wait for a longer time. It's better than to use X-rays. Neutrons and X-ray are opposite, so in that sense.
Cool. Thank you very much.
Thank you once again,
Okay.
Dr. Larrea. Okay, so our next guest will be Paula Sanz Camacho. She did her PhD in the University of St Andrews in Scotland, working on the synthesis and study by solid-state NMR of inorganic materials, in particular heterocycles of phosphor and selenium. Then she moved on to the topic of sodium-ion batteries, and she went to France to the Institute of Condensed Matter Chemistry in Bordeaux for several postdoc positions. And since early 2024, she is a senior researcher working on sodium-ion batteries in the Department of Electrical Storage in the Iberian Center of Research in Energy Storage.
To invite me to this talk. Today, I would like to tell you about how we use local techniques. In this case, I will talk more about solid-state NMR and a bit about Mossbauer spectroscopy to study the effect in cathode in sodium-ion batteries. So I will first like to introduce the CIA, which is a new center in Spain that maybe some of you don't know. Then I will briefly introduce sodium-ion batteries that was mentioned and speak in the first talk. And I will talk about solid-state NMR a bit. And then I will explain two studies that I have done in polyanionics and in Prussian blue analogs. And I will finish with some conclusions. So CIA, it is a new center that has been created in 2022 in Cáceres. It is analogous to the INL that is in Portugal. It was a Spanish and Portuguese initiative with 80 million initial funding. Nowadays we are in the Polytechnic of Cáceres, but normally we will have 3 different buildings. This one, the pilot plant, it is already been it is in construction, will be finished in spring of 2022, and the main building is going to be finished in 2026 normally. So I will just explain the different departments we have in CIS. So I belong to the electrical storage department, but we have also an hydrogen department and a thermal department. So we study different technologies. Then we have also transversal lines that help us. For instance, we have prototyping, we have modeling, and we have life cycle analysis. And we also have the pilot plant. We have 5 of them, one in flow batteries, in hydrogen, thermal, in circular economy, more recycling, I would say, and microgrids. And this pilot plant is allowing us to go from the TRL low that we are doing in research to a higher TRL. So again, I will just mention briefly the context of sodium ion. So as we all know, because of the replacement of fossil fuels, because of the climate change, it has been a lot of increase in the lithium resources needed, especially for the battery field. We passed from, in 2010 to 23 to 71 in 2020. We all know that lithium, it is not very abundant, that it is also, the reserves are located in the lithium triangle between Chile, Argentina, and Bolivia, and that mostly the refining is done in China. So this is why we want to, it's been a lot of driving forces to study different technologies, more sustainable. Amongst them, sodium, as it's been mentioned, has similar chemistries. Also, it is more sustainable because it's more abundant. We try to use no critical raw materials, especially cobalt, and this also has an impact in the low cost, and they are safer technologies. So just the three materials in the cathodes that stand out for their performance and that has been studied is layer oxide and polyanionics. That is especially the layer oxide is being mentioned by the first speaker. But we also have the newcomers here that it was the Prussian blue analogs, that they are porous frameworks, and I will explain later on more in detail. So all the families, they have advantage and disadvantage. None of them are perfect. For instance, MBPF has problems with sustainability because it's used especially vanadium, but they perform as well as PBA quite good in ray capabilities. In the case of the negative electrodes, there is so many effort in finding a good negative electrode, but for now on, the one that is performing the best is actually hard carbon. And just to see the market in the world of this technology, well, there is some startups that has been focusing to this technology. In China, there is much more that I mentioned here. There is even a car, as is being mentioned. And in Europe, there is 3 companies working in this technology. We have Atris working in Sweden, working in PBA. We have Faradion working in UK in layer oxide. And we also have Tiamat in France working in the polyanionic material. So solid-state NMR, it is a very powerful tool. It is give information about the local structure of the nuclei of interest. As we can see for the periodic table, we have quite a lot of available nuclei that we can study. Usually what we do is that we put our solid material in a rotor, we put it in the magic angle spinning, and we spin fast enough to remove all the anisotropic components that we have in solids. And this technique is allow us to study different aspects. We can study amorphous, for instance, defect, polymorphs, dynamics. In the case of today, I will also mention that we can study paramagnetic compounds, but we have an extra interaction here because we have paramagnetic elements containing electrons and pair electrons, and so we have a hyperfine interaction that it will especially shift our signals, so we will observe very, very shifty signals in the spectrum. And well, we can use this study in the case of cathode for study the local structure of the pristine material itself, the sodium, if it's in prismatic or octaedral, and so on, if there is presence of defect. And also we can do study the mechanism of intercalation if we stop at different potentials. So the first study I wanted to show you is this family of cathode, which is MBPF and MBPF-O. So they are interesting because they have high theoretical capacities, and we can extract 2 sodiums. So in literature, it has been a lot of discrepancies in the crystal structure of these materials, so especially of the MBPF. Some of them were saying it was tetragonal, some of them they were saying it was orthorhombic, which has an impact on the different crystallographic sodiums and phosphorus sites. And also, the phase diagram was not well understood because some of them was saying it was solid solution and some a two-phase reaction. So what we did here is we tried to, we partially oxidize this to the MBPFO, and we study different materials here. So we passed from a totally fluorinated one, we substitute the oxygen here, and we also study the totally oxidized one. And we do this by phosphorus and sodium solid-state NMR. So the first thing that we notice in the spectrum of the totally fluorinated is that we have two signals. One, as I already mentioned, very shifted, and one that we didn't know. In the literature, this was attributed to the fact that it was in a tetragonal symmetry, so we have two phosphorus sites, so it was assigned like that. And the same for the sodium. However, when we do the different partially oxidation compounds and the totally oxidated one, we see that actually these signals correspond to the oxidated also versions. It was appearing in the same position. And actually, we determined by this work that this was not two different phosphorus sites, but it was defect that it was present in the totally fluorinated one. We were also able to attribute the signals of each spectrum, and in fact, it is because we have partially oxidation, so we have vanadium 3, vanadium 4, and so the phosphorus environment see in some cases 3 vanadium 3 and 1, or 2 vanadium 3 or 1, and that's explain the whole different signals. The same it is in the sodium spectrum. We observe different signal corresponding to the partially oxidation of the compounds. And how this translates into the electrochemical properties of the materials? Well, by here we compare all of them, so the series from fluorinated, totally fluorinated to partially until 0.5 and to the totally oxygenated ones. We can observe that the fluorinated and the oxygenated ones has a biphasic behavior, while the intermediate case, the partial oxidated, is more a solid solution. And also we can increase the capacity when we partially oxidize, and there is also a change in the reduction potential. So this shows that small changes in the composition actually have an impact into the electrochemistry, and that we can tune it nicely by synthesizing different compounds. So the second family of material I want to show you today is these Prussian blue analogs. So these Prussian blue analogs are porous frameworks. So the structure is, as you can see here, we have different transition metal connected by the cyanide group, and it has channels in the structure that is allow the introduction not only of sodium, but also potassium and some also divalent cations. Depending on the synthesis conditions, there is also the presence of vacancies and the presence of crystalline water. And so we talk about Berlin green when we don't have, for instance, any cation inside, about a Prussian blue when we have a medium content of the cation, and about Prussian white when we have a rich content of the cation. And we can see that actually it's passed from a cubic structure to a rhomboedral or monoclinic structure when we have more content of the cation inside. So when I first started studying this material, I see that it was three main phases known in literature to be Prussian white. So the first one was by Teófilo Rojo. It was cubic, and it was done by a coprecipitation method. Then it was an hydrothermal one, rhomboedral one synthesized by hydrothermal synthesis at 140 degrees by Gudenov, is the one that it was performing the most, and is the one that actually is is studied by altruists, this rhomboedral phase. However, the reproducibility of the synthesis in this case was not possible. I tried to synthesize this by this paper, and I didn't manage. But actually, you can synthesize the monoclinic. That's what Palanivalaya did. He synthesized the monoclinic that is contained 2 molecules of water, and you dehydrated the phase and remove the water, and it's formed this rhomboedral structure. So I decided to study the synthesis of this material to see if we can find new phases, and also to understand better how the parameters and the morphology is changing also in these materials. So I synthesized the qubit phase, follow the similar reaction than Teófilo Rojo. I also do a study on the hydrothermal synthesis of this material that is allow us to find a new phase here, orthorhombic phase, also rich in sodium. And I study the temperature, how that does affect the phase form. I compare also this with the monoclinic phase that Palanivalaya in collaboration shifted to us, and we transformed this into the rhomboedral structure, and we compare all in this study. So the first thing we notice is that the coprecipitation, because of the quick reaction of the 2 solution, is precipitate rapidly and is form nanoparticles, while in the hydrothermal, which is done by acidic decomposition, we have more like cubic phase, cubic particles, not nano, around 1 micrometer, and a bit bigger for the reflux synthesis. So I studied this by Mossbauer spectroscopy, which is a technique that allows us to understand the coordination of the iron, the spin state, and also the presence or not of defects. So we noticed that for the coprecipitation and for the reaction hydrothermally at 60 degrees, we see the presence of iron 3+, so it's suggesting that we don't have a Prussian white structure, while, for instance, the orthorhombic, the new phase orthorhombic, and the monoclinic and rhomboedral is present at 50% of low spin iron 2 and high spin iron 2, what is expected for the ideal structure. We also notice that this rhomboedral phase has distortion in the high spin iron 2+ here, and we believe this is because by removal of the water in the structure, it is also kind of deformed. So we performed some electrochemical charge discharge of this material. So the first cycle, we noticed that the 2 compounds synthesized at 60 degrees, it has less amount of sodium, so it's suggesting, as I already mentioned, that we don't have a rich phase, while for the others, we have almost 2 sodium extracted. This strange behavior of the orthorhombic is still under study, because we don't understand why we have this behavior. And, well, we noticed that the capacity of the orthorhombic is a bit less than the monoclinic and the rhomboedral, but it's still an interesting compound because, first of all, it's not air sensitive, and we still need to improve the performance of this material. So I would like to finish the conclusions to say that small changes in the composition has an impact into the electrochemical behavior, that it is important to understand the relationship between the synthesis, structure, composition, and electrochemical properties, and then local techniques such as NMR, Mossbauer, and DFT together. It is a good tool to study this defect. And so this work I present is during my postdocs in France with these people here in the ICMCV and the ICGM. And this is the funding here, and I would like to thank the CIA team now in Cáceres. And thank you for your attention.
Thank you for your presentation, Paula. The organization has agreed to let this be the last presentation before the coffee break. So now, if anyone has a question, of course.
Thank you for the nice presentation. Just one question. There is a lot of interest about the disordered material, rock sales. I mean, how the technique NMR can help to disclose what is going on with the disordered material?
Well, NMR, I actually studied some of the rock salts by NMR because they can tell you about the environment of sodium or lithium, depending on the presence in the layer or in the intermediate space. And so if you have some disorder, I think you can see it by the local environment of sodium, for instance. There is some studies being shown.
You have a different ppm.
Yeah, I think just you have maybe different signals, and also you have different environments, maybe. I mean, it depends on the specific case, but yeah, you should have normally local change in the environment should have an impact into the shift in the NMR. Yes.
Thank you.
Any other quick question? If it's not the case, then once again, thank you, Doctora Sanz Camacho. And we can now proceed with the coffee break. So see you all again in 30 minutes. Okay, so dear guests, let's move on to the second session. We will be starting with the due presentation of Professor Yaniv Sanchez. He's from the University of Grenoble. He obtained his PhD in Montpellier in 1972 in physical organic chemistry and got a postdoc at the Institut Européen de Membrane, where he performed in pioneering researches on electron conducting and mixed electron ion conducting polymers. He became an associate professor at the Grenoble Institut Polytechnique in 1984, and ever since he has continued his scientific career. He has made a lot of publications, over 180 or something. He has also been a professor here at the University Carlos III de Madrid, and his researches are dedicated to electrochemical energy sources, and he has supervised 3 European Union projects and a 10 of national and regional projects. So.
Thank you very much for your presentation, and I did not provide you information, so it's all information, but more or less is exact. So thank you, thanks to Bidan and Alejandro for inviting me to participate in this meeting and to deliver a lecture. So I'm afraid the topic that I will speak about is far from the preoccupation of most of the audience. So I will try to be a little bit didactic. So regarding polymer and salt for lithium battery and beyond, I mean post-lithium battery, I will present our selection, one of our present selection. This can be changed. Excuse me. So first, we will have a look at something that is very important, but I can say that about only 10% of the activity in the field of battery is related to the electrolyte, and is the activity that is mainly focused on electrode materials. And something that is very important for lithium-ion batteries and beyond is macroporous separator. So I know that people use some kind of fiber-like membranes that cannot be used in a real battery. And what we have in battery are what is macroporous separator. So people say often, and me by the past also, microporous, but in terms of UPAC rule is macroporous regarding the average diameter of the pore. This is a CellGuard 2400, and yeah, is the thickness of is 25 micrometers, obtained by a dry process and by extrusion stretching with an average porosity of 41%. This is polypropylene based. This is polyethylene based, ultra-oriented polyethylene of very high molecular weight. And this is 57 micrometers thick. Is obtained by a wet process, by trying to stretch the material during the process to increase the order and therefore the crystallinity of the material. And something that is more, that is safer is the three-layered CellGuard 2325. That is a three-layer of polypropylene, polyethylene, and polypropylene. Once again, the average, the thickness is 25 micrometers, and the porosity 39%. You can see polypropylene, polypropylene, and polyethylene. As the advantage, what you can use, you can manufacture the lithium-ion battery without any electrolyte, and then fill the battery at the moment to sell the battery with liquid electrolyte. So you have not self-discharge during the storage of the battery. That is an advantage of this kind of material because they do not change. There is no significant shrinkage, for example, of the material following the filling by the liquid electrolyte. They have also another quality is very high mechanical strength, and that is due to the semi-crystalline polyolefins, both polypropylene and polyethylene. Also, what you can obtain with this kind of material in case of a dramatic event is a shutdown effect, a shutdown with the pore clogging. As the material cannot be swelled by the liquid electrolyte, if you clog the pore, you have a dramatic increase of the ohmic resistance of the electrolyte and to stop the battery event. This is, for example, polyethylene melt at lower temperatures than polypropylene, and at melting around 110 degrees, it can fill the porosity of the polypropylene layers. The drawbacks that you have of the material is a sharp conductance decrease. If you try to measure to determine a kind of conductivity with respect to the conductivity of the liquid electrolyte, you have some often factor 10 to 20 in the decrease of the conductivity. And this is important. Also, you have an anisotropy, because material being done, for example, in a process with stretching, in machine direction, you have a Young modulus much higher than in the transverse direction. And you have also a low filling kinetic. When you want to introduce the liquid electrolyte, it takes a lot of time because to get the filled material. And the questions that we can have is what about the safety of this material when you reach 170 degrees, that is roughly the melting point, the higher melting point that you can get with polypropylene, and the material becomes a kind of a candle, melted candle. So that is a question. So I will go, now I will change and I will go to solvent-free. These separators are useful for all the mobile electronic PC, cell phone, etc. But now if we look at lithium battery and battery for electric car in general, one of the problems is the safety issue with low flash point of the liquid electrolyte. So I will speak about polymeric backbone, so polyoxyethylene base electrolyte, and with some recall, because the audience is perhaps not used to use this kind of material. In this kind of material, the polymer is hosting a salt. So you have a multifunctional performances of this material, a solvent functionality. It replaces the mixture of carbonate that you have in the liquid electrolyte. And this is in charge of the salt dissolution. You have to eliminate all OH group because they can react with the negative electrode. And so therefore the material has a few solvating ability versus the anion, a low acceptor number. In terms of polarity, you have a much lower polarity that you have in classical liquid electrolyte because high dielectric constant is associated to also high viscosity, and in terms of polymeric material, in terms of strong dipole-dipole interaction, so a great stiffness of the material. So the driving force of this material is mainly the high solvating ability versus the cation, the high donor numbers. So, and the problem is that the mechanical properties of this material, once after melting the semicrystalline phase. So we have to combine that, what I call squaring the cycle, to get high mechanical strength combined with high segmental mobility. And we will give some information about that. So first I will speak of the salt. The salt can be used in polymer, but they can be also used in liquid electrolyte, for example. And we have addressed some years ago this aniline-based sulfonamide salt. And the idea is to extend the delocalization of the negative charge in order to favor the anion-cation dissociation in the ion pair. And so we did, with this kind of material, a series of material in which R1 substituent in auto position is, in most of the case, is H. And in R2, we used H, fluorine, CF3, nitrile, and NO2. And with the reference, excuse me. So as professor, I think that I am able to speak to speak sufficiently without the loud form. But the number has respectively 1A, 2A, 3A, 4A, and 5A. And in R1, we used one with nitro. The nitro group also, in order to have a dinitro compound. And to host this polymer, we use a material that we have experienced that have fairly good mechanical properties, and it is obtained by polycondensation, and giving this material with unsaturated moiety that allow to cast the film easily, and then either by solution or to extrude potentially this material. And in the last step, to crossing the material thanks to a photoinitiation and UV irradiation. I will call that NPC 1000. So what I went to, something that perhaps recall you something about your organic teaching during your formation, your background. And this is, you can see that you have a strong delocalization through the P bonds of the aryl group and up to the nitro group. And so if you look at the canonic form of this, you can get a lot of delocalization of this negative charge. And this is an asset to decrease the basicity of the anion. And so I have represented there the conductivity that we can get a reduced plot, conductivity of this compound, and you can see that roughly the conductivity increases with the electron withdrawing effect of the group. For example, nitro group is a strong electron withdrawing group, and the higher conductivity are indeed obtained with this salt. And more or less, it follows the value of this value are mesomeric effect, and this is already known. We have value data. And now if we go to the cyclic voltammetry and the anodic stability, you can see also the different groups, the different voltammetry of this. And you can see, for example, that all are compatible with the use, for example, of sulfur cathode or LFP cathode. And the best one, the dinitro one, is perhaps able to be used with LNMO cathode. So once again, you have an increase in anodic stability when you increase the electron withdrawing effect. In terms of physical organic chemistry, there is something that has been very used in the introduction of the knowledge of kinetics, is the the rho sigma Hammett relationship, that is a linear free energy relationship involving thermodynamic constant. And in that value, sigma minuscule, sigma p and sigma p minus, and overall sigma p, is indeed the pKa of benzoic acid. So something very easy to get as formula, and you have this value as tabulated for a lot of electron withdrawing and electron donating group. And when we plot, I have changed in capital the sigma of the conductivity in order to avoid any confusion. And when you plot this one, excuse me, you can see that you have an excellent linear free relationship between the pKa of the Hammett pKa and the value of the conductivity reference to the unsubstituted material sigma h. Sigma h, and this is sigma x. X can be nitro, nitrile, and something. And you can see a good correlation. And this Hammett type correlation demonstrates quantitatively that ion pair dissociation, therefore the ionic conductivity, is governed by the ion basicity. To the best of my knowledge, this is the first proof of concept, quantitative, regarding the basicity. So the lower the anion basicity, the higher the conductivity. Now we did the same with the potential, anodic peak potential, and you can see once again that you have a good correlation with both sigma p and sigma p minus. Sigma p minus is a factor that is a kind of parameter that are very interesting, whether you have a direct interaction between the negative group and the electron withdrawing group. So once again, the lower the anion basicity and the higher its anodic stability. Regarding the cationic transference number, hosted in this material, we did that by electrochemical method, either Sorensen or Peter Bruce and all method, or by pulse field gradient NMR. And more or less, we have not exactly the same value, but they are not so far in that case. But what we can say about that is that T plus, the cationic transference number, decreases along with the extent of anionic delocalization. More you have delocalization, and lower will be the T plus, as in TFSI, which is very low. that is in TFSI is about 0.1. Okay, okay, excuse me. So now we like to speak about semi-interpenetrated network. Semi-interpenetrated network, the main asset of that is to combine an existing polymer that is really cheap, polyoxyethylene of high molecular weight with our previous NPC 1000. And the main interest is the cost decrease. And also, a second point is that it allows to have film casting easier during the process due to the entanglement of the long chains. So what can be done is that the effect of semi-interpenetrated network on POA chain dissolution is that the entanglement between the entanglement between the long chain and the network result in a decrease of the solubility of POA in water. POA is highly soluble in water at ambient temperature. And you can see that for 75% of POA, for example, you have only 30% that dissolve after 24 hours immersion in water at 40 degrees. So regarding the conductivity, we can get nice conductivity with this material, in particular at 75% of POA, at 2 concentration, oxygen over lithium 20 and oxygen over lithium 30. And this is interesting for both, in particular at 75%. Now, if you go to dynamic mechanical analysis of these ships, you can see that the POA alone breaks at about 60 degrees, 50, 60 degrees. And, but there is no creeping when it is associated to the cross-linked material, NPC 1000. But the modulus range between 1.3 and 3.5 megapascal, and for us is not enough. So we use in order to reinforce the material without losing in terms of conductivity, we use nanocrystalline cellulose for this material. So with at 6 and 12% of nanocrystalline cellulose, a little bit of this was lost, of conductivity was lost, but not so much. About 5 to 10% of conductivity was lost. But in that case, we got a neat reinforcement with on the rubbery plateau and up to the degradation of the at 250 degrees of nanocellulose to storage modulus of about 40 megapascal. That is enough to decrease, and we can guess that it's possible to get a thin film of 10 micrometers of this material, so increasing the conductance.
Janine?
So up, I think I have to
conclude. Could we
that.
please? Okay.
So I will say that electrolyte is an essential topic, but is neglected. Neglected for liquid, because in solvent something very interesting have to be done, but people remains with LP30 and similar commercial liquid electrolyte. I think the topic of solid polymer electrolyte is an interesting multidisciplinary research field. And I hope that it will convince some students to go in this field, because there is in part of that it gather organic and macromolecular chemistry, physical chemistry, material science, and also the objective is the electrochemistry. So also it offers a great challenge. There is a great challenge. Instead, for example, POA is not adaptable to NMC, for example, because the anodic stability of the polymer matrix is not enough, but a huge possibility of innovation. And sorry for the delay, not long, I overpassed. Thank you very much.
Does anyone have any question, like quick for Jean-Yves? If you think it could take long, I would suggest to...
I am not from the same field, but it's just a very broad question that when we have to deal with polymers, could you help us say which are the main properties that we have to look at it?
I think, excuse me, I think first in all the system, what is essential is to get grid safety. I am afraid that batteries that are developed in all the world now for electric car with a lot of disaster in terms of fire, something will ban the electric vehicle. I am afraid of that. And I think it's essential to pay attention to that. For that, in this kind of system, you cannot use you can use the porous separator, but it's not adapted. The porous separators are very expensive. If you get, for example, 1 kilogram of polypropylene at €1 per kilo, you can get a price at up to 1,000 and more euro by kilo for the microporous separator, made of the same material. So that is very important. So the safety also, and if you can get very thin film, this is interesting because people are focused only on conductivity. What is important is the conductance. If I can make thinner, I can decrease the ohmic drop in the electrolyte.
Thank you, Professor Sanchez. So our next ponent is Maria Carmen Asensio. She is a distinguished researcher professor at the Institute of Material Science of Madrid. She earned her PhD in physical chemistry in the National University of La Plata in Argentina. She has held positions in prestigious places worldwide, including the Autonomous University of Madrid, the University of Warwick, and the Fritz Haber Institute of the Max Society in Berlin. She developed a groundbreaking electronic spectroscopy technique known as nano-RPs, nanoscale angle resolved photoemission spectroscopy, which gave unprecedented insights into electronic properties of materials. And in recent years, she and her team have integrated artificial intelligence tools into their work to accelerate the discovery and optimization of materials for renewable energy applications. So, whenever you want.
Thank you. Thank you. First of all, thank you for inviting me here because I was working in Madrid for many years. I've never been here before, and it's a very nice campus. Thank you to the organizers for inviting me and allow me to tell us a bit which are our interests now. Well, let's see how it works. This, yes. My talk here, it will be a bit didactic because it will touch several subjects, but of course, we can take later a bit more deep in each one of them. The idea is really to face the problem of accelerating the discovery of novel materials for energy materials, for mainly batteries. What is the problem? As we will see, we have a very big escape of chemistry associated to this type of batteries. And then the problem is to find the best one, the more performant, that can really answer our needs. Well, just to present myself is Maria Asensio. I'm working in this group, Greener, from the Institute of Material Science. The Institute of Material Science belongs to the CSIC and is in the campus of the University of Madrid in Canto Blanco. As well, we have a very close collaboration that we call Matinee. It's an associated research unit with the University of Valencia. That means that we are having we can share people and instrumentation with the University of Valencia. And we are really organizing now a conference in June. We will invite you, all of you, to visit Valencia. It's a wonderful city, close to the beach, very nice in summer. Anyway, let's go. This is the Institute of Material Science, and the content of my talk will be more or less like that. We will go through briefly about an introduction of energy material, low energy materials, because now we have nanostructure in everything, in almost all the components of the batteries. We will go through just the chemistry associated to the lithium-ion batteries and the components, and how we can use particular techniques to characterize these components. You know, the characterization, the electronic and chemical characterization of these materials is essential in order to really go forward in the performance of the batteries. And for this, I will talk just a bit, because we don't have too much time, about conventional techniques and how you can complement this technique with nanoprobes and chemical imaging in large installations like synchrotrons and neutrons. Some examples, just we don't have too much time, but I will show you some examples of this, and how you can characterize chemistry and electronics, because so far this morning the people were concentrating in a structure, and a structure is very good, but as well sometimes the chemistry it can help to characterize the components of the batteries. Finally, we will talk about the artificial intelligence, how this tool, this new tool that is dedicated to materials now, can help to develop all these other aspects like characterization and performance of batteries. We will talk a bit just about different algorithms. And then, you know, the first is the need to really develop energy materials that can help us to have friendly energy sources. We have every day more an increase in these demands, and it's not easy to resolve it with the actual sources. The important thing that we have learned is that we cannot just rely on one type of energy materials, on one type of alternative energy source. We need to combine all of them. But, you know, batteries are very important because can help that the next between them, because these other sources of clean energy, like solar cells or wind, is fine to get the energy, but we need to storage it. And battery is really you know, it's a key aspect in this circle that we are trying to get. Just to summarize, we have different components, and as already has been mentioned, we have not just different components, but different mechanisms. We have for example, we have insertion of lithium from the anode to the cathode and the cathode to the anode, but as well we have cathode and anode with conversion mechanisms, which are really related with a chemical reaction, where a big change of volumes of the components of the cathode or the anode is changed, and then we have to manage all this when we make cycling, the cycling of the batteries. And then all this make that we can organize all the materials related with the mechanisms that are working on the battery. For example, convention cathodes present more specific capacity. They can reach a very high, but of course we have the problem of the chemistry that is there, that normally is very complex and very difficult to manage. As well, in the anode, for example, we have a very good candidate with silicon anodes, and the people are pushing a lot, working, trying to make it available in the market, silicon that can be used. However, the silicon as an anode have a very big increase, about 300% increase of the volume of the silicon when it's lithiated respect to when it's not lithiated. And then it's very difficult to keep the mechanical integrity of the anode after the cycling of the anode, because this big increase of volume really perturbate the, the mechanical properties of the anode. This type of problem we gain in the specific capacity, but we lose in many other properties of the component. And that's happened exactly the same in the cathode, you know, and in the electrolyte. And then we really find out that if we search in all the components, here we have cathode, anode, electrolyte, and in different generations, we were first working with NMC, NCA, for example, LFP, and with we increased the time we were improving these materials. For example, you know, for the people that are not used to this type of nomenclature, the NMC are just this type of oxide with nickel, cobalt, and manganese, and the numbers correspond to the stoichiometry of each one. And then we were from less content of nickel, 111, to now 811 or even 911, where we have mainly a component of nickel, and we improve the performance, but we lose other properties. And then this historical evolution of the compositions of the components of the batteries show us that we start with LFP that was not very good cathode in the sense that didn't give a very high energy, specific energy, but it was very reliable because we could cycle batteries for a long, long time. And now initially we lifted this and we improved the NMC, but nowadays there are building companies just based on LFP. That means that this summarizes the problem we have, for example, for cathodes. These type of cathodes are the more known, but we see that if they are very good in energy, they are very poor in cyclability or sustainability, and you know there is an equilibrium. For this reason, it looks like that we are stuck in this. We have a big chemical space to choose, and we cannot get the best candidate that can be better than the actual components. And these components, we were in the market for more than 15 years. Now, the laminar and nanomaterials or layer materials, like 2D material, this is a summary of the 2D materials that we were dealing with, are introducing another aspect, very important, because can nanostructurate the cathode and the anode. These are very nice because we have very big families, like, for example, TMD, that are transitional metal decalcogenized, or these are transitional metal tricalcogenized. They are really perfect layer materials, and when you introduce these materials on the massive volumic other components, they structurate and get better performance. And then there is a big trend, an important trend in people trying to nanostructure the component, but industrially it's very difficult to manipulate nanomaterials, and then it's not easy. Anyway, now we are able, even in the lab, to manage materials practically atom by atoms. The problem is not to produce it, because we can produce it by solar shell or other procedures. The problem is to characterize them, because they are very small and they are very difficult to manage. For this reason, we need synchrotron radiation sources. This is an escape of the synchrotron radiation in the world. We have mildly concentrated in States and Europe, and now in Asia, for example, just in China, nowadays are building more than 10 new sources of synchrotron. And that is funny, because the first one were the Americans, the second were the Europeans, and as these were the first, now these synchrotron in US are very old, are not very good in shape. But in the Europe, we are concentrating now the best synchrotron sources in the world. Probably in a few years will be concentrated in China. Just to, it was what we think that the answer to the characterization of component of batteries is just to combine conventional laboratory techniques that we can use in the lab with this type of sources. These are some of the Europe, Electra in Trieste, close to Venezia, Max Lab in Sweden, ELLS and SRF in France, LS in Berkeley, and ALBA in Barcelona. There are just a few of the synchrotrons that most has been used to characterize materials. But what is this? You know, the speaker in the morning, we're talking about the diffraction. This is just a summary that we can find when we interact light, X-ray with matter. We have diffraction, as has been said, transmission, diffusion, absorption, fluorescence, and photoemission. With this technique that are all together when you interact matter with light, you can get important information about the elementary specificity. You can really know quantitatively how many elements you have in your sample, the oxidation state, I mean the chemical information, the valence bands and the reactivity, stability, and of course, with diffraction, the structure. That means the position of the atoms in the matter, and then you can follow the transition phases of the processes. Normally, what we do in a technique, in a synchrotron, we choose one of these techniques. For example, in my case, I was working with photoemission, and you don't take the detectors, you don't use the detector of the other ones, but you have to be aware that always they are there, and actually the fact that has been mentioned this morning that the damage of the focus of the spot on the sample should be taken into account because it's very, very important. Anyway, I will just show you one example that was very interesting. You know, is absorption in a battery that is really working now. And then this is absorption means that you have an X-ray that is coming. You have a sun plate that can focalize the spot of this X-ray, and then you can illuminate just a short spot of less than 1 micron, okay, less than 1 micron. And then you can scan all around your sample and get this image, actually, or similar image we will see, detecting what the X-ray part of the incoming beam has been absorbed. This is an absorption technique, and if you plot these absorbance, you see that around the core level of iron, you can identify the red and the green like iron 2 and iron 3. And then when you have this H here around 708 EV, you have iron 3, and when you have the H or the peak in 305 approximately, you have iron 2. And then that means that if you measure this, when you cycle your battery, you can really see the transformation between lithiated and non-lithiated species. And then you can get this information, microscopic information, around the whole part of your cathode and see how the lithiation goes. For example, green means iron 3 and red means iron 2. I mean, you can follow the lithiation at different speed of the cycle and see what your behavior, the behavior of your cathode is going. It means that this is just for summary that the techniques that we can have by hand now in Europe, because the access to large installation is free for all European people, you can just ask for time and you can access to these tools, is very, very fine. It's very good, and you can really get very detailed information, spectroscopic, quantitative, chemist, and I would say almost everything. But even that, even if you manage that and you can really collaborate with groups in order to get all this information of your sample, you have difficult problems to really get the right material. Because normally the right material you have to choose. You have many candidates to choose, and then it has been measured that approximately when you start to work on one material, since that you start until you apply in the market, it passes approximately 15 years. This is the normal history of more or less all the material that has been developed in the past. And then the idea is try to use not just experimental study of material or theoretical simulation that has been the traditional approach, trial and error. I will take this candidate, I will study, I will try to see if I can improve it and use it. But as to this scheme of trial error, just to ask artificial intelligence approaches. What is this? Well, you know, we have to learn about what is it, because the most powerful company in the world are dedicating a lot of energy and money and effort to develop this artificial intelligence for materials. And then we see, for example, that Google, DeepMind, Microsoft, Facebook, that has changed the name, I don't know, but you know, DeepMind, for example, has produced density functional studies, not traditional, but helped by artificial intelligence. That means that now, with this approach of artificial intelligence, you can do a full study, theoretical study of DFT in a few minutes instead of weeks or more. And for example, Microsoft has calculated properties of these materials, of any materials, on basis of algorithms of artificial intelligence. As well, diffusion, for example, in crystals. For example, Facebook has worked on catalyst, and you know, they have produced very nice piece of work already using, accelerating the process that has been used traditionally just with artificial intelligence. But what is artificial intelligence? Well, we have different areas where the artificial intelligence in general is just a program that first there is a statistic analysis of the data that is available, and from that they get some tendencies how the behavior of these materials are, okay? And then this is like always the same: explore, learn, and growth. And then in machine learning, that is subgroup of these algorithms are the same that are the general artificial intelligence, but are improving themselves as much as more data that you give to these programs. And then if the big programs are increasing, the algorithm is learning from the size, increasing the size of the data. And deep learning, it looks like a neuron strategy where you have layers and each layer intercommunicate between them. But anyway, what is proposed is this. You know, you start with artificial intelligence, you get databases, a lot of bases, and we will see how many and which are the main databases available open now. And then with this and some theoretical study, after this you get a list of candidates. I'm sorry. After these three, you know, you have a methodology where the first phase is a framework based on artificial intelligence. This is alimentated by databases. These databases already exist, and they are very big, and they contain experimental and theoretical data. Then you can make your theoretical calculation or simulation as you used to do. And then with this, you get a list of candidates, which are the best materials that can be studied. And with this list, you go to the synthesis and characterization and, of course, the testing of the cells. This is more or less the scheme of the approach that we are proposing in our studies in our group. And then just a few words about the data collection. You know, there are data collection of gravimetry analysis, optical properties, solubility, toxicity, electrochemistry. You can interact with this, and these data are coming from experimental data. They are just programs that they call meaning like, you get a mineral. You get information from all the papers that have been published so far. That means all the papers that you publish can be accessed by these programs, and then they get the information and then enrich these databases, okay? I told you, for example, in Europe, you have NOMAD, that is is proposed by the European community. Now has already 11 millions of materials has been integrated the NOMAD database. These are more specific open quantum materials for low-dimensional materials is of the order of 1 million of material. Material project is very well-known material where really even the people that are not using artificial intelligence are consulting because it has been created by the government of Obama in US. And then there is a very nice, in Berkeley, there is a very nice platform that allows you to get information about experimental theoretical properties of material associated to only batteries, okay? And then these sources, these databases are open, means that you just have to get into that and ask for information. And then what we have worked in our group is just a set of codes that can do with artificial intelligence two types of things. One is prediction of properties of materials, okay? Just get this information from the database, organize, and I ask you, what is the energy formation of this material? And the program gives me the value, okay? Estimative value, virtual value is not a real value, it's a value that is given by the artificial intelligence code. But it's a guide. I not pretend that it will be exactly with a high precision, but give me the guide. And then with this, I can use different codes of machine learning that we call supervised learning, unsupervised learning, reinforcing learning, that are more technical names, but it doesn't matter. The important that are codes that are not complex, are open, that you can use it, really, in order to calculate property of materials. And then, we have as well, yes, generation of new materials. You can generate materials, okay? And then we have put all together in the platform in which you can have access because it's open. And this is the link to visit it, where we have the databases, I describe it, but we have the way to access to this, visualize this data from the database, make some calculation, and then get the artificial intelligence codes. You can use this tool just right now, just asking for permission. And then, these are the possibilities that you can do. You can access to the data, you can see the data, you can make some calculation, for example, transport electric or transport ion materials or any optical properties, and you can generate new materials just by generative modes like substitutive or prediction. This is the platform. You have to ask for permission to get in. If you get in, you can get this type of part of the platform. You see here discovery of materials, property of materials, and then you just can choose elements in the periodic table and say, well, tell me how many compounds have with silicon and lithium. And then you get this, for example. It has been evaluated 2 million of compounds, and the platform has found 6,700, and then you have the list, and you can visit them, you can learn about them, okay? How it works, this is just informative, but the next step is to get a new material that it doesn't exist in the database. And for that you get the latent space. What is the latent space? It's this one where every point is one compound from the database, organized following the way that they behave. If they are good cathodes, they are bad cathodes, they are separated. The good cathodes are in one area in a cluster. And then you see that are all blue, but there are green, that, this cluster, at this point correspond to compounds that behave similarly. And then we have put here the good cathodes that we know, NMC, the traditional one. And we see that around them, there are many other compounds that should behave similar. And then these are the new candidates that we are investigating, okay, more or less. This is just very fast because we don't have time, but this is the center of the idea. And then just concluding, material science is essential for future technologies, and we need good technique of characterization, and of course include the artificial intelligence, and just a knowledge of all my group at the ECM, at the Valencia University, and the international collaboration. Thank you very much.
Gracias por tu presentación, María. Does anyone have any questions regarding this presentation?
Hi, thank you very much. That was a very interesting talk especially about AI, as important as it is now. My question with these AI databases and programs moving forward, because they're allowing you to help investigate new materials and develop new materials, do you think they have the potential to investigate the compatibility between two materials? Like for interfaces between, electrolyte and cathode?
You can tune all this. For example, so far we have worked new cathodes, and we have found one new cathode without cobalt, without nickel, and with 30% more capacity than NMC 811. And that was our first experience, and we did it in 2.5 years. And then now we are going to interfaces, and we are going to the problem of the change of the volume. You can face any problem of the batteries or any other type of problems. The only thing is that you have to find a good descriptor. What is a good descriptor? A property that is sensible to your problem. And then if you give to the code, improve this descriptor of this property, the code will work in a sense to improve this parameter. But we can discuss later on, but really it's very wide the way that you can approach many problems. For example, I am a specialist in photoemission and address particularly the interfaces problem. I know what is the interfaces problem, but experimentally you can go to a limit. You cannot go farther. It's very difficult. And then you need a guide. And the guide, for example, could be thermodynamical stability of compounds that can be found at the interface, for example. And that you can manage with the code of AI, artificial intelligence, with much more grounded basis than experimentally,
Thank you very much.
So if anyone else has any other question, maybe quick, or if not, you could save it for another break. Okay.
Yeah.
Okay.
Yeah.
you need, I mean, the person should be have some programming knowledge. I mean, you have to write a code, or the software, if I put my descriptor, for example, I want to improve optical properties, and then it will give me the list of...
You know, there is a platform that we were developing in parallel with the development of our project, and then we have opened it, and the idea is that it's public, and you can access to the databases, you can access to some calculations, but it's open. You know, if you want to calculate some particular property and make a particular search more complicated, we are open to collaborations as well. You know, there is a minimum level of activity that you can do with the platform yourself, alone, without any problem. You can access, you can copy, you can learn a lot. But of course, if you need development, you know, you need the collaboration with the team that are are developing the platform. And then you can be in contact and we can stabilize. You know, we offer public and collaboration, academic and as well consulting to companies. There are some companies that are very interesting and has contacted us, and we are working for companies as well.
Thank you once again, Professor Asensio,
thank you
for your interesting topic. So let's continue with Paula Navalpotro Molina. She is a chemical engineer with a master's degree in renewable energies and a PhD in electrochemistry from the University Autónoma de Madrid. She has 10 years of experience specializing in redox electrolytes with organic redox materials and biphasic immiscible systems, focusing on their application in innovative concepts such as supercapacitors and redox flow batteries. She's the co-author of 16 scientific articles published in high-impact journals. Additionally, she is the co-inventor of 3 patents licensed to private companies. Currently, she's a postdoctoral research in Marcilla Group at the Institute India Energy.
Thank you for the introduction, and also thank you for the invitation to give a talk. I'm going to change the topic a bit because today I'm going to take this opportunity to tell you the latest results that we got in the field of redox flow batteries in the electrochemical processes unit in India Energy, and specifically in membrane-free redox flow batteries. But first, let me do a brief introduction about redox flow batteries, since it's the first talk on this topic. A redox flow battery is the unique type of battery that is able to decode energy and power densities, and that makes them very interesting to be coupled with renewable energies, solar farms or wind farms. And this characteristic is mainly due to the special configuration that these batteries have. In these batteries, the active species are dissolved into the electrolytes that are stored in 2 external tanks, and these electrolytes are pumped through the reactor, where the electrodes are located and where the reactions are taking place. And the reactor is divided into compartments by an ion selective membrane. Currently, the state-of-the-art, or the most studied one, battery is based on vanadium chemistry. And vanadium has some drawbacks, like it is a critical raw material and some of the species are toxic. And also other, let's say, problematic component is the Nafion membrane, that it doesn't avoid totally the cross-mixing of the electrolytes. And also, if we look at the cost, we can see that these 2 components are one of the most expensive ones. Membrane can be up to more than 40% of the total cost of the battery, and also vanadium species up to almost 30%. So with these drawbacks in mind, of these challenges in mind, we propose a different approach, that is the development of a membrane-free redox flow battery. We don't use membrane because instead of that we used immiscible electrolytes. So the electrolytes are in contact, but they cannot mix like oil and water concept. Also, we replace the metallic vanadium species by organic redox molecules because, well, they have some advantages, like they are more abundant. It can be synthesized in a conventional lab, and we can functionalize the structure to change some properties like the redox potential or the solubility. Regarding the nature of the electrolytes, this concept can be also quite versatile because we can have different configurations and we will have different battery characteristics. We can have two non-aqueous immiscible electrolytes, having more, probably more energy density, but also more environmental concerns, or a combination of aqueous and non-aqueous of electrolytes, or even having two aqueous electrolytes, having a more sustainable and safer combination. And we are focused on this specific combination. So the first step is just having these two aqueous phases. And for that, we used aqueous biphasic system that, for those that are not familiar with this concept, is just an aqueous solution of two solutes. These two solutes can be two polymers, one polymer and a salt, or even two salts that above certain concentrations, the system is split up spontaneously into aqueous liquid phases. Here you have the phase diagram, so depending on the concentration of the solutes, we can have two phases or just a normal solution. These systems have been applied usually in separation and extraction processes, but we are now applying them in batteries. So we have to take into account, in order to select those solutes, the electrolyte properties that we want, like viscosity, conductivity, polarity, or even pH. So we have tested several different biphasic systems, but today I'm going to show you the results for this specific example using polyethylene glycol, a polymer, and a salt. Here you have the phase diagram. So we select a point here in the biphasic region, and we will have two phases, two liquid aqueous phases with this composition. So the next step, we have the two aqueous phases. We need to convert them in a battery. And for that, we need to select the organic redox molecules. They should fulfill different requirements. Of course, they should have different redox potential, as large as possible, to maximize the energy density of the battery. But one very important requirement here in this concept is that they should have different specific solubility, because we don't have a physical barrier to keep them separated. So we are going to separate the active species just by thermodynamics. They should show then higher affinity just for one of the phases. So one of the species should be soluble in the top phase and the other one in the bottom. And of course, they should have reversible and stable electrochemical activity. We did a screening because we have used different active species, but today the example will be focused on this ferrocene derivative for the catholyte, the positive part of the battery, and a biologian derivative for the anolyte. So we have the active species, we incorporate them into the biphasic system, and we observe that they are selectively separated by thermodynamics. There is no any type of separator between them. So we measure this separation by UVB analysis, measuring the partition coefficient, and we observe that the ferrocene derivative is going preferentially to the top phase, and the biologian is going to the bottom phase. So yeah, we can keep them effectively separated without barrier. Then we test electrochemically the phases separately, and we obtain the expected behavior, because these species are already studied and reported, are not new ones. And so we have the redox reaction expected for the biologen and for the ferrocene derivative, having a different difference in voltage around 1.1 volt. We also do some studies about the kinetics and diffusion parameters. And then the next step is having a battery. So for us, it's easier, or it was easier to test the battery in static conditions first to see if the system behaves as a rechargeable battery. The assembly is really easy and simple. In a glass cell, we merge one electrode, one carbon felt in each of the phases, and we characterize the battery. And we observe that, yeah, the system behaves as a rechargeable battery. You have clear charge and discharge plateaus with a different contribution of the top phase, the bottom, and the interface. We have an operating voltage close to the theoretical one, and also in the cycling test we have quite a stable performance. So, okay, the next step, we test the battery in static conditions, but our goal is having a flow battery. So the next step was developing a new reactor, because we cannot use, as you can imagine, the conventional filter press reactor. We developed a new one in which you can see here in the image, we can control the interface, the natural liquid-liquid interface between the two phases. And we, again, characterize the battery. And yeah, we obtain quite a stable performance, and we can keep the interface at the desired position. But we observe that the efficiency is not very high. And this is mainly due to the self-discharge reaction. This is a drawback of the membrane-free concept, that is the self-discharge reaction, that is an electron exchange reaction that occurs at the interface between the generated species. So we charge the species during the charging step, but these species can diffuse and meet at the interface and undergo a reaction, a recombination reaction, and come back to their initial state. This self-discharge reaction is limiting the efficiency of the battery, of course. So we start to think about different strategies to minimize this self-discharge. And one of the strategies that we are using is the hybridization. So here we replace one of the dissolved species by a zinc metal foil. And in this way, we are avoiding the contact at the interface between the species, since zinc will be in solid state. So for that, we need to reformulate the biphasic system, because now we need zinc ions in the solution. And we select these two salts, zinc chloride and lithium TFSI. We add into the water, and we have here the phase diagram. So we select a point here in the biphase region, and you can see here the biphasic system with the natural interface. We have the active species in the system. We have the zinc that is already there, and also we keep the same catholite species, the ferrocene derivative. As you can see just by naked eye, it is almost soluble in the bottom phase, so the separation is almost total. And we characterize the phases, and well, we obtain the plating and stripping of the zinc and the expected reaction for the ferrocene derivative with a difference around 1.2 volts. So the next step was characterizing the battery in static conditions, this hybrid battery. And what we observe is that, yeah, we have again, clear plateaus for charge and discharge. We have an operating voltage close to the theoretical one, and the most important thing is that we have quite high efficiency, Coulombic efficiency between charge and discharge. So we are avoiding the self-discharge. We cycle the battery, and we observe that at some point this Coulombic efficiency starts to fluctuate. And this is mainly due to the dendrite formation, that the dendrites growth and touch the interface and then start to reduce this efficiency. To demonstrate that that was the reason, we changed the anode by a fresh one, and we recover the smooth and stable performance. So the next step was to make the system flow, to have a real flow battery. For that, in our design, we did a very small variation. Just we changed one of the carbon felts electrodes by a zinc foil, and we characterized the battery again under flowing conditions. And we observed that we are keeping the plateaus, the clear plateaus, and the good efficiency that we have, and over cycling we are able to have a stable and high Coulombic efficiency. So we have a quite high capacity utilization, almost close to the theoretical one, having good efficiency and stable performance, and well, the flows is mitigating that dendrite formation. So just to conclude, we have formulated these redox aqueous biphasic systems or electrolytes, and we have applied them in membrane-free batteries in static conditions, also addressing one of the main drawbacks, that is the self-discharge, and we have developed this hybrid membrane-free flow battery that, as far as I know, is the first example of this kind of battery. And just before finishing, I would like to thank all the members of the Electrochemical Processes Unit, especially to Rebecca Marcilla, and other former colleagues that are also authors of this work. And if you have any question, I will be happy to answer.
Gracias por tu presentación, Paula. Very daring concept, the one you bring here. So, do we have any questions?
Thank you for the presentation. My question is about, I see in the charge-discharge plot that you have a very large ohmic drop. And why this high ohmic drop in a liquid system? Why is in the interface between the...
That is something that we are trying to optimize, and it's mainly due to because in the reactor design that we have, the electrodes are quite separated. The distance between the electrode is almost 1 centimeter. And that is the main contribution for the internal resistance in the battery and the ohmic drop. Yeah, we are trying to decrease that distance and optimizing the performance. But the main contribution is that distance that is very large. But it was a first approach to see the interface, control the interface, and it was the easiest way, let's say, but not the optimum.
Thank you for your talk, Paula. I would like to know if you have found any problem with the mixing of the two phases while you are pumping, because of the speed of the pumps.
Well, we have performed different studies at different flow rates. It's true that if you increase very high flow rates, you can have some perturbation of the interface, but we go to even 60 milliliters per meter, and we don't observe any problem in that sense. Because, well, before doing the reactor, we performed some fluidodynamic simulations and the studies to be sure that we are able to keep a stable interface. Yeah.
Okay, thank you.
I have a question about the use of, first a remark. LiTFSI is a very good salt when it is dissolved in aprotic medium, but it's not good in water because HTFSI is a poor acid in water. So this salt is not the best one. But my second question is, why did you use LiTFSI?
Well, it was one of the reasons is that having the older system that is based on a polymer and a salt, we observed that the viscosity of the phases was quite different, and the phase that is reached on the polymer is the viscosity is really high, and it can limit the diffusion of the species. So in order to have a less viscous and higher ionic conductivity, we select two salts, and one of the salts was lithium TFSI, because in order to form the biphasic system in water, we need two anions with different nature. So TFSI is very different from chlorine. Otherwise, it's really difficult to form spontaneously the biphasic system.
Okay, so thank you once again, Dr. Naval Pedra Molina. And let's continue now with the presentation of Dr. Ignacio Villar García. Ignacio is a lecturer at San Pablo CEU University, where he leads two national research projects on the advanced characterization of metal-ion batteries. He did his PhD in the University of Nottingham and has worked in various institutions, including the University of Addis Ababa, the Imperial College of London, the Institute Imdea Energy, and the ALBA synchrotron.
Thank you very much for the kind introduction and for inviting me to this conference today. Where I'm gonna go a little bit back to the topic of operando characterization and talk about these operando studies of vanadium-based lithium-ion batteries. We keep with vanadium as it seems to be very popular today. Just an introduction to the group. So I work at the solid-state materials chemistry group in the University San Pablo CEU, where I joined in September 2023 with a project, consolidation project to do the advanced characterization of batteries. And I joined this group, which has long historic and good published record on creating materials for batteries, both the synthesis of new materials and their electrochemical characterization. And so we joined forces with my knowledge on synchrotron advanced characterization in order to try to understand the systems that they are developing in a more in-depth way. So the outline of the talk, I will do a small introduction about vanadium metal-ion batteries, and then I'll go into a particular case of this vanadium oxide material, and I'll talk about different operando studies that we have done in order to try to understand in a more detailed way this system. We have already seen quite a lot of XRD and SACs in the morning presentations, and I'm going to add some infrared and XPS to the pool of techniques that can be used in order to characterize batteries in an operando way. So, as you've seen this morning, like the research in vanadium for batteries has increased quite a lot. Some of the reasons are because of abundance and relative price in relation to other elements used in batteries. And another of the important reasons for using vanadium is its rich redox chemistry. There are different oxidation states available in vanadium that increase, obviously, the capacity and the ability of the material to intercalate more metal ions. So in the group, there has been quite a few studies with different vanadium oxides. You can see they have very good cavities, capacities, and capacity retention. And I have chosen initially this material because apart from its good specific capacity and life cycle reversibility, in the group they have found a green, fast, and cost-effective procedure that is very promising for commercial applications. The material has been characterized intensively with both XRD and neutral diffraction, and the structure, pristine structure, is well known to have stacks of V3O8 layers with hydrogen interlayer bonding, and the vanadium coordination is composed of both distorted octahedra and square pyramids. But what's happening to this material as you cycle it in a battery? So for that, we've gone first. So all these operando experiments have been done in ALBA, in the National Synchrotron, based in Barcelona. This first experiment on XRD was done in the MSPD beam line, where you can cycle up to 8 coin cells at the same time. In case of the operando cell that we have used is a typical bottom cell modified with a Kapton window that allows X-rays to penetrate the cell and interact with the material and be analyzed as they go through. So here you can see the discharge of this material, where it goes through 3 different phase domains, like 2 solid solutions and one 2-phase domain. And you can see there that the material structure is expanding in order to intercalate lithiums within this structure, especially in the interlayer spacing. And there is a new phase forming in the 3rd phase domain, but we have not been able to refine these structures yet. So for that, we have gone to a different beam line. It's a Notos, where you can do XRD diffraction and absorption at the same time. So you can use exactly the same type of cells. And in here, you can actually follow the diffraction and so you can follow and here is only the absorption, the X-ray absorption. So you can see the vanadium edge as it goes through the different phases. So in here, there's a solid phase where the material is just expanding a bit. And as you go through the second, you can see a bigger shift into the X-ray absorption. And the beauty of this beamline is that you can follow both processes at the same time. So you can link the XRD data to the absorption data. And what can we see with the absorption? So during the discharge, there is a shift and decrease on the pre-peak that we have seen in previous talks, that it holds quite a lot of information. and it's similar to what happened with iron. The lower this peak, the more centrosymmetric the coordination is. So it means that the distorted octaedra are becoming less distorted as you incorporate lithium into the structure. Another information that you can get from X-ray absorption is that the rising edge, the position of this rising edge has been seen in the literature that is a good measure of the oxidation state, or the average oxidation state of vanadium in this compound. And if you get all the positions and use the calibration that has been done, we can see how the average oxidation state was from the 4.5 average that this material should have to the 3.9 average as you cycle it, as you discharge the battery. But so this gives you just an average value, so you cannot really know if it goes from only 5+ to 4+, or it goes, so you also get 3+ in the material. And in order to investigate that, we've gone to a different building, Miras, where you can do Operando infrared in reflection mode using this special cell where your electrode is facing the silicon window through which you can do these reflection experiments. So if you do the infrared spectrum of the HBO material, you can see clearly two signals for the symmetric stretching of vanadium oxygen, which depending on the energy, they are characteristic of 5+ or 4+. And if you will zoom into this area, we can see clearly like the two signals. And then we start cycling the battery again. And in the first phase, we can see how the 5+ signals goes down and the 4+ starts going up. In the second phase, we see how this 5+ keeps disappearing and the 4+ increases. And in the third phase domain, where we can see the two-phase regions, we can see how now the 4+ starts decreasing and the 3+ oxidation state starts increasing. So the beauty of it is that we can also see it in charging, and we can see that this process is reversible. So we know what's happening in the bulk of the material thanks to the infrared, as the penetration depth is in the micrometers region. Now we want to know what happens exactly on the surface of this material, and for this we use a surface technique, XPS, that gives you information on the top nanometers of your material. XPS is surface sensitive because the signal that you are analyzing, the photoelectrons, can only escape from the top part of your material. This makes it very difficult to analyze it when the material is immersed in the electrolyte where it works. So what we need to do is to try to analyze at the meniscus of the electrolyte, where this electrolyte layer is very small, and we can still see both the surface of the material and the electrolyte at the same time. And this is the cell that we develop, and is happily inside of the ultra-high vacuum chamber. This electrolyte can be inside of the ultra-high vacuum chamber because it's an ionic liquid which has very low vapor pressure, and it doesn't evaporate even at these ultra-high vacuum conditions. And you can see here where the meniscus is at the surface of the electrode. And if you go through this meniscus, you can see you go from no signal to some signal, where you can see both the electrolyte and the electrode. and analyzing at different excitation energies, you can select exactly which point where you get the right conditions to follow the oxidation state of the surface as you cycle the battery. And here is a summary. So you can see initially how you have both 5+ and 4+ characteristic of the HVO material. And as you start decreasing the voltage, you see how the 4+ starts increasing and the 5+ starts decreasing. And then at some point, there is the appearance of the 3+ state, which is more dominant at the end of the discharge of the battery. And now this is just the summary of all the techniques that have been used, that we have been used to understand how this material behaves within a battery. And it only leaves me with the acknowledgements. So I have to thank all the Vinland scientists that have helped us to run these experiments over the last year. And many thanks to the group for their welcoming and making everyday life very easy, and all their research inputs and the financial support that we have in order to run these projects. And thank you for listening.
Thank you, Ignacio, for your kind presentation. Does anyone have a question regarding to this?
Very nice presentation. My question is about when you make this kind of measurements, it's important which cycling rate you use.
We use C20, so all those experiments take over 2 days.
And you find changes when you increase the rate in the phases that are produced in the surface of the cathode, or not? Or it's always the same?
We didn't have time to check different seed rates in the Operando experiments. We just chose one that we are sure that the material behaves. So where you can observe the more changes. So you go to a very high seed rate, then the material, obviously you won't have or not all the material will react to the intercalation of lithium because you don't have enough intercalation. So we choose a very slow seed rate in order to make sure that all the material, or the most of the material changes in this cycle.
Thank you.
Any more questions? Okay, so once again, thank you, Dr. Villar. And now the following and last presentation before lunch break will be done by Habib M. Pafan, and I wish the organizer Bidhan was here because he told me that he wanted to make the presentation for you. But well, your presentation will be now. Yes. Which ones you are covering?
I think Bidhan knows. Give to you.
Bidhan knows it. Let me just inform you. pen drive or by email your presentation?
Yeah.
Let's look for it.
It's okay by mail.
If you want to access there yourself.
Just give me 1 minute.
Okay. No, estábamos intentando hacer simplemente para but you have the USB.
First one. Yeah, first one. Should I start?
No, just give an introduction.
Hello. So let's go to the next speaker. Is Habib Pathan. He's from India, Pune University in India. Mr. Habib Pathan has more than 275 research articles. He has published for international and national patents. His in publication, his H index is more than 44. He till now has supervised 18 PhD students. He has been world's 2% scientist list published by Stanford University and elsewhere for last consecutive 3 years. And he is also an editor-in-chief in ES, Quantum, and Nano. So let's welcome Habib Pathan. Over to you.
Yeah. Thank you very much for the nice introduction. I'm going to talk on the advanced materials for energy conversion and storage towards the sustainable development. The theme of the conference is related to the storage of the energy. I will talk before that the generation of energy, and maybe I think in a successive conference of third one I may cover something learning from this today's conference and may cover something about the storage of the energy. But today I am mainly talk about the conversion of the energy. So the strategy, selection and design here we are used is to have the antenna. Thing is that we have the light from sun which is in the range of 350 nanometer to more than 1500 nanometer. So we need to have a strategy wherein we can use this solar light to convert it into electricity. And we know that if we can use the different materials, there will be the restrictions. For example, if we use a semiconducting materials, we can harvest the few percentage of the light that is mainly from the UV visible and NIR. If we use a lead sulfide quantum dots to harvest the light, we can convert the energy which is greater than this 1 electron volt and so on. So the idea is to use a different physical principles to absorb the entire spectrum of the light from 350 nanometer to 1500 nanometer. So mainly we are going to use the Foster resonance energy transfer process, and this can be achieved with the help of the hybrid solar cell strategies. So my presentation only I will start the introduction, methodology, results and discussion, and then the conclusion. So we know that we are facing the energy crisis. I will not go into more detail about it. So we mainly work on the fabrication of a dye sensitized solar cell and quantum dot sensitized solar cells. In that also we have a energy from the sun, as well as in a auditorium or in a halls we have a light sources from nowadays from the LEDs. And LED has a different spectra of the light that can be effectively utilized to convert the light energy into electrical energy. At present these have the low efficiency, but at the same time a less stability. So we want how to overcome these issues. So we are going to use a hybrid co-sensitization, wherein this will be act as the donor, this will be treated as an antenna, and this will be acceptor as the dye. The routinely used dyes like N3 or N7 can be used as the acceptor, and then this can be act as a donor. So this faster rate electron transfer process can occur only when there is a distance between these two, donor and the acceptor, is of the order of 1 to 10 nanometer. And then this can get the energy from the source, which can get excited, and this will have this FRT, and then you will have the acceptor, so that there will be a more harvesting of the energy by using this concept. So the proposed structure will be like this one. You will have the dye here, and in this presentation we use this gold doped nitrogen sulfur carbon quantum dots. So I will first explain about how we have achieved the gold, nitrogen and sulfur doped carbon quantum dots, and then we have used this FRET and RET in order to enhance the efficiency of these kind of solar cells. So synthesis of gold, the nitrogen sulfur doped carbon quantum dots. The method used for this process is laser ablation. Time is 30 minutes. We have used this laser, and you can see this is the synthesis setup used for the fabrication of the gold doped, the nitrogen and sulfur doped carbon quantum dots. So we synthesize these NSCDs using one pot hydrothermal method. This process involved preparing a mixture with equal ratio of 1:1 citric acid and thiourea. In order to fabricate a hybrid solar cell, we have the TiO2. So this is the conducting substrate, fluorine doped tin oxide coated on the glass substrate. On that we have deposited a titanium dioxide nanorods, and then the barium titanium trioxide, and finally we will have such a structure wherein you will have a TiO2, BaTiO3 as a transparent photo anode. On that we will deposit these nitrogen sulfur doped carbon quantum dots. Then this is usually used dye, N3 dye, and above that you have the gold coated. This is the electrolyte, and then a platinum electrode. So device fabrication, the prepared TiO2 BaTiO3 photoanode were immersed in a N3 dye for 12 hours. Dye sensitized photoanodes dip into this gold coated NaCd solution for 4 hours and dried at 60 degrees Celsius. Photoanodes loaded with dye, gold, NaCds were paired with the counter electrode to form a sandwich structure. these are some fundamental studies of the NS series which we fabricated by a laser ablation process. This is atomic force microscope images. This is size distribution, and this is a transmission electron micrograph to show that these are the particles of the order of quantum dots. This is fundamental study of these carbon quantum dots, XPS study, which shows that this consists of all the individual elements. So this the X-ray diffraction pattern of gold NS series and sensitize the photooners. So you can see that this is the X-ray diffraction pattern of TiO2 and BaTiO3, and this is gold NS series TiO2 BaTiO3. So once this photoanode is fabricated, that will be dipped in a N3 dye. This is Raman spectra of the gold NS series. The D band around 1348 centimeter signifies defects or disorder in the carbon structure, and G band observed near 1585 centimeters per is observed in plane vibrations of sp2 bounded carbon atoms within a graphite structure. So this is FESM images of TiO2 nanorod, and then on that BaTiO3 has been deposited. So the C is a TiO2 BaTiO3 photoanode, and this will show a particle size distribution of this photoanode. This is optical properties. You can see that this one is TiO2 BaTiO3, and then with this the gold NSQDs, you will have this optical spectra, and after sensitization you can say that there is the increase in the absorption in this case. So this is in a visible light, and this is when it shows the fluorescence. So this FRST is calculated to be a 22.17%, and these are the PL with respect to the wavelength. This is normalized luminance with respect to time. As you can increase the concentration of N3 dye, you can see that this efficiency goes on increasing. The fundamental understanding has been done by using this cyclic voltogram in order to find out the HUMO and LUMO of this sensitizer, which has N3 dye plus the AU-NS carbon quantum dots. So LUMO is observed at minus 3.58 electron volt, and HUMO is at minus 6.68 electron volt. So the entire structure, the energy band diagram will look like this one. You have it TiO2 BaTiO3, the combination of sensitizer and the electrolyte and the platinum counter electrode. So this will show you the different configurations and the efficiency observed. So you can see that this is 0.41 without the N3 dye. With N3 you have a 0.84, and with the combination of gold NSQDs and the N3, one can have a efficiency which is greater than the individual one. 1.29 is the efficiency. This is the Nikes and body plot. These are the different parameters calculated for these the solar cell. You can have a longest effective lifetime, superior charge carrier retention, high effective diffusion coefficient, and whereas this reducing the charge recuperation rate and improving the VOC. You can see from here. So in nutshell, we can see that the laser assisted hydrothermal synthesized highly fluorescent gold NSCDs have proven to be an effective antenna material for a hybrid solar cell. When integrated with N3 dyes, these materials resulted in 30% increase in photoconversion efficiency and improved charge transfer properties. Incorporating gold NSCDs into the N3 sensitized TiO2 BaTiO3 photoelectrode enhances the charge recombination resistance. Gold NSCDs can be potential material for future advancement in energy conversion and storage towards a sustainable development. So, this is the recently carried out fundamental study. We have fabricated a different kind of a solar cells by using this N3 sensitized. The indoor efficiency for such a solar cell is more than the 30%. So the main idea that we are working on is we can recycle the light, we can reuse the light and then convert it into electricity, and furthermore we can think of storage this energy. So with this, thank you very much.
Thank you, Professor Pathan. It was a nice talk among all. I think a lot of energy storage battery presentations is an energy conversion presentation, solar cell. So the forum is now open for any questions and discussions. Anyone? I have just one question. Like you are expert on solar cells. So I want to know that what is the future of solar cell in dye synthesized, or this is a long story now, is solid state solar cells or this kind of thing? Like in battery we have like this kind of thing. In future, like is that any?
Yeah, especially when we think about these solar cells, the silicon technology is largely developed for the outdoor application. Whenever we think about the indoor application, the DSSC, that is dye sensitized solar cell, and the quantum dot sensitized solar cell will have a bright future.
And just one more question. How about something like integrating solar cell energy conversion device and battery or supercap as an energy storage device and make a standalone device altogether?
Yeah, the researchers are trying to develop such a device, integrated device, where you can have a solar cell plus the battery or a energy storage device.
But the thing is that why we don't find any commercialization of that? Like in some countries, maybe in Japan or China, they have limited things like street lights or something. But why don't have a big scale or commercial, big production of this kind of?
Obviously, it will take time, but I think in near future we will have a combination of a energy conversion device as a solar cell plus the energy storage device as a supercapacitor, and that will have a single unit with these.
Thank you so much.
Yeah, thank
Anyone?
you.
I guess. So in that case, so thank you, Professor Pathan, for your nice presentation on solar cells.
Thank you very much.
So now it's a long period. Now it's time for lunch break. So after 1 hour and 30 minutes, we'll be back again for the last session. So see you all in the lunch area. Okay? Tickets is with Alejandro. Yes, sir. Maybe some of you will leave after some people, so let's come take a photo in front of them and then we'll. Okay?
You are taking all your
Eso yo creo que está conectado. Espérate, agua igual tenemos aquí. We can wait 3 minutes. ¿Estáis usando el micrófono en las secciones o no? ¿Pero estáis usando? ¿En la mesa? Sí, estamos usando, pero no hace falta eso. No, ¿se oye? ¿Se oye? Sí. Por si acaso. Ah, te lo he movido, perdona. Perdona.
Cuando tengo en la cabeza no se te ocurre.
Vale, genial. Gracias.
don't know where is the chairman, but in case we are going to start. So the next speaker is Manuel Belmonte. He comes from Institute of Ceramic and Glasses from Madrid. He's from the CSIC. And he's going to talk about 3D printing, the use of the 3D printing just for materials, energy materials.
Okay. Thank you. Good afternoon. Thank you, Alejandro. Thank you also for inviting me to give this talk. It's a pleasure to be here. Well, today I would like to show you how it's possible through the use of additive manufacturing technologies to provide some solutions in the energy field, in particular by developing thermal energy storage materials and also 3D catalysts for hydrogen production. So let's get started. Well, it's not necessary to mention the huge worldwide problems that we have in terms of energy and environmental issues. Thermal energy is one of the most appealing energy sources to reduce the greenhouse gas emissions and the dependence on fossil energy resources. Among the different technologies, thermal energy storage is one of the most interesting because the efficient use and the storage of thermal energy. Actually, we can find many different applications where contain TS units. For instance, in the recovery and subsequent reuse of waste heat in industrial sectors, such as the production of aluminum, concrete, cement, ceramics, and glasses, in building heating and cooling applications, especially in the outer surface of the building. Also in the aerospace field, and there is currently the Parker solar probe that goes to the sun, and it includes a TS unit inside the probe, and also in the nuclear energy as a safety unit. In this case, it's covering the vessel, and in case there is an unexpected shutdown of the reaction, and the temperature starts to increase, that amount of temperature or the heat can be captured by the TS unit while the problem is solved. It's released down the cooling system or whatever. But the most interesting, the most common application for TS is the concentrated solar power plants, which use the world's most abundant renewable energy source, that is the sun, can dispatch power even during the night time. It's a technology highly efficient and with long-lived storage. There's no CO2 emissions during operation. This is very important because rare earth or special minerals are not needed, that you know that is so critical right now, and of course it's scalable. So within the TES, latent heat storage is one of the most interesting, which is based on the phase change enthalpy of the material within a narrow temperature range. From the different latent heat storage, the most important or most interesting are the solid liquid phase change material because they are standing properties such as superior storage capacities, limited volume changes. They cover wide temperature range from room temperature up to more than 1,000 degrees C. But there are some problems associated with this PCM. For instance, the liquid leakage. Despite they are into containers, typically metallic containers, sometimes there are liquid leakage in the molten state that reduces considerably the efficiency, and especially we employ high temperature PCMs, typically molten salts, that are commonly employed in most of the applications that I previously mentioned. There's also an important issue related to the corrosion with metallic containers. So to overcome these problems, some years ago, researchers proposed the PCM encapsulation by developing form-stable composite PCM. In essence, they mix the PCM in the solid state, in powder form, with some other powders that contain a porous microstructure, such as expanded graphite, nanotubes, graphene, mesoporous silica, or some others. So they mix it together, they heat it till the melting temperature of the PCM, then solidify, and they got a specimen or pellet or whatever, a compacted pellet containing both the material and the PCM. With that approach, they were able to reduce the liquid leakage, not always, but at least in a certain way. But there are also still other problems, such as low mechanical strength, low corrosion resistance, and low heat transfer rate. This is especially important when you use molten salts, because the corrosion is quite important with carbon-based materials or also metallic-based materials. So our approach is to employ the additive manufacturing technology to produce highly porous pattern supports. What we can do with additive manufacturing is to tailor the porosity of the structure, enhancing the mechanical strength, increasing the surface area, and hence the heat transfer rate. And that is combined with ceramic materials to develop ceramic support. That, as you know, ceramics present low density, and they have high temperature resistance, good chemical, and high corrosion resistances. So it's perfect for both combinations for the goal that we have. So the goal is to develop novel TS, that we call 3D TS, by infiltrating with molten salt 3D printed cellular ceramic structures. And in the mean term, beyond this goal, the aim is to fabricate elementary bricks for the design of a next generation of volumetric solar energy receiver for concentrated solar power plants. So essentially what we use as additive manufacturing technology is robocasting or direct ink writing technology, where the filaments are continually extruded and deposited in a layer by layer sequence. The technology is quite versatile, low cost, and easily scalable. We can print multi-material, which is very good. And the key point here is the ink, the printed ink. So we need a special rheology of the ink, specifically pseudoplastic behavior for fluid-like consistency during ink flow. The inks that typically are in water media and aqueous-based media have high solid volume content with low organic contents to reduce the shrinkage and cracking phenomena during the further thermal treatments to consolidate the structure. So before going to the main topic of the talk, just mentioning briefly, during the last, let's say, 15 years, in our group, we have manufactured many different kind of structures based on oxide ceramics, such as zirconia, alumina, also cubic yttria, non-oxide ceramics, such as silicon nitride, silicon carbide, aluminum nitride, max faces, pure graphene, carbon-based materials, composite ceramic graphene, etc., for a wide scope of applications, such as heat transfer and thermal management, catalyst for wastewater treatment and synthesis, acoustic metamaterials and oil-water filters, supercapacitors, and hydrogen production that I will mention during the last minutes of this talk. So you can check in our webpage the publications and the materials that we have developed in the last, let's say, 10 years. So let's move again to thermal energy storage materials. We selected as a supporting material expanded vermiculite clay. It's a low-cost material, highly absorbent, with a laminar structure that you can see here in the micrograph. Is formed by the flakes. That could probably enhance the infiltration degree of the PCM, let's see in a few minutes, and also present high temperature and corrosion resistance. That is ideal for our application, considering that we want to work with molten salts. So we used two combined approaches. On the one hand, through the pattern design of the structure, and on the other hand, increasing the porosity into the clay skeleton by adding a porogen or pore former into the ink. So we formulated our ink in aqueous-based media with vermiculite. In this particular case, we didn't incorporate organic additives, so it's just water, vermiculite, and a certain amount of activated carbon that we employed as a pore former. So finally, we got a pseudoplastic ink. I'm not going to go in detail about the rheology of the ink because it's not the scope of this talk. But what I can say that with that formulation, we were able to build robust clay architecture with filamentary shape retention. So this is the starting point. This is a typical pattern design from the very beginning. We designed cuboids of 12 by 12 by 5 cubic millimeters with vertical open channels that should be around here, but also without external wall to promote the building of horizontal channels to enhance the infiltration into the scaffold. So once we printed this design, we heat treated at 800 degrees C in terms of to mechanically consolidate the scaffolds, but at the same time trying to keep as maximum porosity as we can into the structure to promote infiltration with the PCM. So the images corresponds to the top and lateral view of one of these scaffolds. This is the width of one of the design, the channel, 2.5 millimeters. The diameter of the filament is 0.5 millimeters, with a total porosity around 90%. So we designed many different options. Here just show you some ones. We modify the width of the channel, the shape, the size, a lot of things, the emitter of the filaments, etc. So let's keep with this first two, where the total porosity is scanned from around 90 till to 92.6%, with a 3D porosity value that corresponds to the pattern design between 65 till 73.5. And those structures were infiltrated with sodium nitride. This is our PCM. Were infiltrated at 350 degrees C for 20 minutes. And afterwards, we calculate the encapsulation capacity of that salt into the support. So the encapsulation was around 85, 87%. If you check now one of these scaffolds that we call 3DTS, from outside, it seems that the scaffold is fully infiltrated by the PCM. The PCM is this translucent phase. In brown is the clay skeleton, okay? But we don't know exactly what's going on inside the scaffold. So for that purpose, we employed X-ray computed tomography, and here I show you some examples of bidimensional cuts where the blue corresponds to the PCM, the sodium nitride, and the yellow is the skeleton, the clay skeleton. So you can see that the PCM already filled the open vertical and horizontal channels of clay supports. If we check now the front surface view of one of these 3DTS, this is the fracture filament of the vermiculite surrounded by the PCM, and a high magnification of this interface between the PCM and the rod evidences that the PCM already penetrated around 50 microns into the laminar structure of the strut. Actually, you look at this field, you can see here the PCM filling the spaces between the vermiculite flakes. So that enhances also the encapsulation and, of course, the energy storage parameters. So as I mentioned at the beginning that one of the main problems with PCMs is the liquid leakage. So we tried to check if we have leakage or not. So what we did was to run up to 10 drains of these 3DTS up to 350 degrees C, so it's heating up, cooling down. We measure the encapsulation capacity once more, till 10 times. So as you see here in this plot, the encapsulation capacity decreases during the first 5 drains, just 2.5%, which is pretty low, and then kept constant with the number of drains. But even the number is very low, we wanted to check or to know from where it's coming from. So if you back to the original images of the scaffolds, the top and lateral view, while you see here some accumulations in the outer face of the scaffold. This transparent, translucent face is the PCM, and after the 10 drains, it's clean, the outer surface. But inside, we have still fully infiltrated with the PCM, so there's no PCM leakage inside the pattern structure, which is pretty good news. So in terms of energy parameters, we calculated the enthalpy of fusion and checked the thermal stability by this DSC. The plot shows you the typical melting and solidifying temperature for the sodium nitride into our structures. With that, we can calculate the enthalpy of fusion, which was 153 joules per gram. The value for the pure salt is 178 joules per gram. And with those numbers, we can calculate the energy storage efficiency, which was around 90%, which is pretty high, because 100% means that we have just pure PCM, nothing else. No scaffolds, nothing else. So 90% is very good value. So we also checked the thermal stability with 15 cycles at 350 degrees C. As you see, the enthalpy of fusion in red and the solidification in blue kept constant with the number of cycles, so the stability is pretty good. And here I wanted to show you the comparison between reported values for a foreign stable PCM based on sodium nitride reported in the literature in terms of the enthalpy of fusion versus the encapsulation capacity. This is our value, one of our materials. So first, as you can see, there's a linear tendency of the enthalpy of fusion with the encapsulation capacity, and our material exhibits very high latent heat storage with no liquid leakage, which is the best news here. But anyway, we are in the top rank of the materials. All of them are based on powder mixture, except this blue data that corresponded to work reported by somebody that he employed silicon nitride aerogels. So this is the first work using additive manufactured structures. We also calculated the energy storage density that contains 3 terms. Two of them, the blue and the red, correspond to the sensible heat storage in the solid state and in the molten state, and both are linked to the specific heat with the temperature. And the third term is related to the latent heat storage that corresponds to the phase change that we were talking about in the previous slides. So with that, we calculate the Q parameter in this temperature range between room temperature up to 350 degrees C, with a value higher than 600 joules per gram, which is superior than most of values reported for form stable PCMs based on sodium nitrite that you can find in the literature. Another important parameter here is the thermal conductivity, because it's closely linked to the charging-discharging processes. So PCMs exhibit very, very low thermal conductivity, typically below 1, 0.5 or something like that, depends on the PCM. So in our case, our material exhibited thermal conductivity of 1.1 parts per meter per Kelvin at room temperature, which decreases down to 0.6 parts per meter per Kelvin at 270 degrees C, that is close to the operating temperature in the real life situation. Anyway, we have a good heat transfer rate. And the next step, no, sorry, I missed this one. And here I wanted to show you again a comparison between the reported values for materials containing sodium nitrite, the thermal conductivity versus the energy storage efficiency. So if we consider that for a practical application we need at least an efficiency higher than 80%, we can create that window where there are just 4 data. One of them that corresponds to our material that stands out due to the remarkable combination with very high storage efficiency, 90%, with a thermal conductivity that is 30% higher than the second best material. Obviously, you can find here other materials with a higher thermal conductivity by doping them with silicon carbide or other conductor, semiconductor materials, but conversely, the efficiency is pretty low, around 50 or even less. So the next step was to check, to validate these 3D tests and the real concentrated solar radiation. We did that in collaboration with our French colleagues in Pyrenees in France. For Promes CNRS, there is a solar concentrator installation which is extremely large. This is the big one, the biggest one. And there is another smaller one in the lab for testing the materials using a solar parabola of 1.5 meters of diameter. And the first challenge here was, this is our original cuboid specimen. So the first thing we needed to do was to upscale the dimension of the scaffold 5 times in height, 2 times in the diameter, well, in this particular case, are cylinders instead of cuboids. The second challenge was to get the same encapsulation capacity that we got with the very small specimens. We got it too, and then we tested in the solar concentrator with solar thermal conversion response. But there is still a problem. The thermal conductivity is still low to have a high efficiency in the process. So we are working right now in that topic, trying to enhance the conductivity of the whole structure. During the last minutes, I would like to move another field, in particular hydrogen, for the decarbonization of all sectors of the economy. You know probably this graph that shows you what is the hydrogen demand in the next decades. That is mostly due to the transport. One of the main problems that hydrogen has is a low energy density per unit volume. So to transport the hydrogen to the service points, we require large volumes of hydrogen to combine a substantial amount of energy. And in addition to that, it's not so easy to transport that because we need a special conditions in terms of pressure, temperature, and so on. So our approach is to produce hydrogen from the hydrogenation of liquid organic hydrogen carriers, in particular formic acid. Formic acid has a renewable origin, is low flammable, biodegradable, and stable under ambient conditions. So here the approach is, let's move or let's transport the acid formic to the service point, for instance, a hydrogen station. So when we need the hydrogen for a car or for whatever, we complete the catalytic reaction and we got the hydrogen. So with that, we have developed an innovative technology called hydroformic. You can check in this webpage our technology in collaboration with the Chemical Engineering Department at University Autónoma of Madrid for producing clean hydrogen from formic acid under ambient conditions, room temperature and 1 atmosphere using 3D printed catalysts. In essence, just briefly, we printed this kind of a scaffold based on activated carbon. And once we consolidate the scaffolds, we impregnate it with a precursor, palladium precursor, and after reducing our treatments, we got 5 weight % of palladium attached to the surface, not only the external surface, but also in the inner channels of the scaffold. Because the scaffold were patterns, as this you see here, with a porosity around 80%, something like that. So with that, we got CO-free hydrogen production. You see here the bubbles of the hydrogen, with a selectivity of 100%, a conversion of the formic acid higher than 80% at room temperature. That can be improved till 100 if we increase the temperature to 55 degrees C. But the idea was to do it under temperature conditions of the ambient. The catalytic stability is pretty good, and we can recycle the 3D catalyst. After a few uses, we can use a mild thermal treatment to reuse the scaffolds. And well, I believe that is out of the time. That's what I was wanted to mention today. Just acknowledge to the funding, and of course our colleagues, Dr. Quintanilla from UAM and Dr. Falcon from Prometheus and RS in France. And that's all. Thank you for your attention.
Thank you, Manolo. Now it's time just for some questions.
Very nice talk. The question is about when you make the scaffold, you present different designs of scaffold, and you choose only for the porosity, the available 3D porosity, but you don't pay attention to the mechanical properties or the thermal conductivity properties of these different designs. So is interesting or not? Or?
Yeah, we check everything. I mean, the first thing is to enhance the total porosity and the 3D porosity. Obviously, if you create a channel like this, it's easy to fill it with the PCM, but at the same time, if you get the melting temperature, it's so easy to remove the PCM. If you make a channel like this, you are not allowed to infiltrate the channel with the PCM, and probably you just encapsulate, let's say, 40%, and it's easier to keep it inside. So you have to play with the dimensions to fill it, but avoid the leakage. That's the first point, okay? The second point is, as you mentioned, the mechanical property. We measure the compressive strength of all the structures. We don't need to have so high values, just to have enough value to handle, and depending on where you are going to use the structure, to have a certain structure. But the porous scaffold, before the encapsulation, obviously are weaker, but when you encapsulate the PCM, it's a block. So we have 70 megapascals of compression strength, which is, I mean, you need a hard hammer to break it. And the thermal conductivity is the other point, of course. Clays are not so good conductor. They have other very nice properties, in terms of corrosive resistance and whatever, but they are not so conductor. So the thermal conductivity of the whole system is around 1 watt per meter per Kelvin. Therefore, most of materials that are reported is pretty good, but it's not good enough for the practical application in a solar station. So that we are doing right now is to replace the vermiculi by other thermal conductors. There is another problem. When you print, you have porous filaments. If you have porosity, despite you have diamond, with in terms of thermal conductivity, if you have porosity, the thermal conductivity goes down so fast. So you have also to play with all those parameters. You need high thermal conductivity, but also need porosity. And you have to play again with the filaments dimensions. You have, let's say, filaments with 1 millimeter diameter. Probably you are going to encapsulate just a crown surrounding the borders, but inside you have a high porosity and the conductivity goes down. If you make filaments of, let's say, 200 microns, probably the mechanical properties are weaker and broke during the infiltration process. So there are a lot of process or parameters that you have to manage. Thank you.
Okay. Is there another quick question and quick answer, please?
I don't know if I'm going to be able to do it.
It's only a curiosity,
Yeah,
because I don't know
go
much
ahead.
about this, but is for the leakage, is it important how well they wet, so the host, and so because you're talking about volume, but also how they wet, is it a parameter that you contemplate?
We check the wettability, of course, but the wettability is linked not only with the material, but also with the roughness and the porosity. So maybe initially you think that your material, the wettability is great, and you see that it's not so great because you have to modify the surface. So it's another parameter you have to check.
Okay, thanks.
Thank you.
Thank you very much. Now we have moved to the flash session.
So that's all the presentations from the invited speakers. Now we are moving towards the flash presentations for the participants. So the first flash presentation for Martha Santos. She is from ICTP CSIC Spain, and her topic will be ion transport properties in free polymer membranes for redox flow batteries. The presentation.
Okay. Okay, thank you for the introduction. I am going to present a part of my PhD based on a work called Ion Transport Properties in Fluorine-Free Polymeric Membranes for Redox Flow Batteries. So, first of all, a brief overview about my topic. Well, the increase in global energy demand is leading to an increase in CO2 emissions, mainly due to the consumption of fossil fuels. So, to try to overcome this scenario, we must triple at least the production of energy from renewable sources. However, renewable energies face the problem that they depend mainly on natural factors such as wind and solar light. So they are non-continuous sources. They provide intermittent energy, so we must store it. So there are different types of energy storage systems, but today I want to focus on electrochemical energy storage and focusing mainly on batteries. So in this other graph, in the graph on the right, you can see different categories of batteries, but classified in terms of discharge time and power capacity. But today I am going to focus on flow batteries, which fall into the category of energy management. So one of the main advantages of these systems is that they can decouple power and energy, as we have seen in a previous talk in this morning, and they are a good alternative for stationary applications. So how do this battery works? Well, as we have previously seen, a redox flow battery consists in two external tanks that contain a redox active material, which will be pumped into the electrochemical cell. This cell is divided into two symmetrical parts divided by an ion exchange membrane. This ion exchange membrane is one of the key components of the system because it ensures charge balance in the system, and also it prevents both electrolytes from mixing. So the three main properties that we want to have in an ion-selective polymer membrane for a redox flow battery will be conductivity, selectivity, and stability. If we have these three properties, we will ensure ion transport in the battery, we will prevent electrolytes from mixing, and we will prevent capacity losses in our system. So nowadays in the market we can find perfluorinated membranes such as Nafion, which is known for its high conductivity and chemical stability. However, the complex synthesis of this material and the high production cost, also the fluorine environmental concerns, are leading to different researchers to find another alternatives for another polymeric membranes to implement in these batteries. So in this work, we are proposing new hydrocarbon polymeric membranes, which have a easy scalable synthesis, a low-cost production, and they are fluorine-free. And also these materials gave us the possibility to modify them post-synthesis to adjust their properties to our application. Okay, so in this slide, I have put a little scheme of the synthesis we are following. The polymers we develop in our laboratory are synthesized via a polyhydroxyalkylation reaction between two monomers, isatine and biphenyl in the first case, and in the second reaction we use isatine, biphenyl, and another monomer which is called Evento. So after the polymerization, we can post-modify the polymers introducing a sulfonic group to make our polymers hydrophilic in order to use them in aqueous redox flow batteries. So we obtain different polymers with varying degrees of sulfonation. You can see in the table that they go from 20% of sulfonic groups to 75%. The polymers were casted and we obtained membranes with a thickness of around 30 micrometers. All the membranes were tested under acidic and neutral conditions and they saw good stability, and also the thermal stability went up to 400 degrees. So once we have our material, we want to test it in a redox flow battery, but to do this, we first have to do some experiments, and we want to focus on three main properties. The conductivity, we will look at it using electrochemical impedance spectroscopy, the ionic and selective transport properties, which we will look at by permeability studies, and finally the storage capacity retention and membrane performance in the cell, which we will try to test it via half cell studies. So the first results I am going to show today are the ionic conductivity measurements. We measured the different samples using Swagelok cells. All of them we measure lithium conductivity in our membranes because we want to test the conductivity of lithium chloride because it's going to be our electrolyte. So in this first graph in the left, you can see how the sulfonic groups, which are the one of the sample in light blue, the conductivity is enhanced due to these sulfonic groups. So this made us make the hypothesis that these hydrophilic groups promote the formation of water channels within the membrane, promoting the movement of ions in our membrane. And as we can see in the right, these are the samples that we measured, and you can see how, as well as the sulfonic content increases, which is the number that goes in the name, 75 correspond to 75% of sulfonic groups and 30 is the less modified material. You can see how the conductivity increases as well as we increase the sulfonic content in our samples. So moving on to the selective transport properties, we performed some permeability studies based on ion diffusion dialysis. This is a very easy experiment to test. It's based on a experiment setup that consists of two tanks, one that contains a feed solution, which is going to be an aqueous salt, and the other one a permeate tank, which is filled with distillated water. So we have a gradient in concentration, so ions will go from the feed solution tank to the permeate tank, and if we register the evolution in the ion concentration in the permeate tank, we can have the permeability values that are going across our membrane. So in the first graph, you can see the transport of the different salts in the experiments. As you can see, lithium chloride, sodium and potassium chloride have a good transport across our membrane, while the membrane showed a rejection of transport to the higher of the molecules of higher size, such as ferricyanide. So this means that our material is working as a molecular sieve. And in the graph in the right, I have just graphed the different samples that we have tested and the different sulfonic content. We have it in the x-axis, and you can see how the permeability is increasing as well as we increase the sulfonic content. So we will want to focus on these two materials to implement it in a redox flow battery. So finally, we chose a membrane to use it in a redox flow battery, which was the one modified at 65%. And we performed some half-cell studies. In this case, we used lithium, ferro, and ferrocyanide as redox active species. And we want to focus on the capacity and the polarization of the curves because this gives us an idea of how our membrane offers the resistance in this system and if it's suitable for making a full cell test. So as you can see here, we were able to cycle up to 60 milliamperes per square centimeter, reaching maximum capacities of 60 milliamperes per hour, which is more or less at 80% of the maximum theoretical capacity. And we were able to cycle up to more or less 70 cycles till now. So to sum up, I would like to highlight the following conclusions. First of all, sulfonated polymers were synthesized using a superacid catalyzed polyhydroxyalkylation reaction, leading to a low-cost and scaled-up material. A direct correlation was observed between high conductivity and sulfonation degree in comparison with the pristine precursors. The sulfonation also demonstrated high permeability to small cations while reduced crossover to larger active molecules, and as we have seen, high stability and capacity retention was achieved in galvanostatic cycling. And now we are focusing on enhancing this sulfonation degree. We are trying different synthesis methods, and we are trying to have better results in terms of this without compromising transport and mechanical properties of the material, and also trying to implement some full cell test. And that would be all. Thank you for your attention.
Thank you, Martha. You have a very nice presentation on redox flow batteries. So now the forum is open for questions. Any questions? Yes.
There's more suggestions than a question. Perhaps you have to try to, if you want to increase the ionic sulfonic group content while keeping high enough mechanical properties, should perhaps try to move, because you do polycondensation reaction, to some kind of block polycondensate in order to have the ionic group in a hydrophilic part and the other part that maintain the mechanical strength.
Okay, thank you for your suggestion. You mean like introducing a monomer that it's already sulfonated and
I think you should look at the work of department of Alejandro Alvarez group, of Teresa Perez Prior, that did alternated block colymers.
Okay.
And in that case, you can maintain mechanical strength while keeping this high content in hydrophilic group.
Okay, thank you. That's a good suggestion. We will try.
So, any other questions? I have a small question. Is slide number 9? Yes. So, at different currents, you have different porosities. Polarization.
Yeah.
So at 20, the polarization is less, which is okay. And 40 and 60, the polarization is almost same. Even capacity is almost same. So there seems like, so means why even 40 and 60, the polarization is the same. So means that's my question.
Yeah. The polarization of the membrane is one of the things that we are facing more problems with because as well as we increase the current density, we lose capacity. But it seems like we were able to cycle up to 60 milliamperes per centimeter, and it was the same as 40 milliamperes. These are experimental results, and this is what we have observed. We have to perform more tests because this also depends on the flow rate you cycle the battery, because if you increase the flow rate, you can also reduce the polarization. So maybe at this flow rate, which was 60 milliliters per minute, maybe the polarization is more or less the same, but...
Okay, and then maybe you will do some tests more and to confirm, okay. There's only one thing, another, that the data resolution here, it started with 0 and suddenly goes up, and even at the end also, maybe you should take more data in that regions, right? Like, it looks little like sudden increase.
This in the level. Yes.
Yeah? So because of the data region, it looks like some artificial kind of graphs.
Okay.
Maybe, you know. Okay, that's my
Thank
question.
you.
Thank you. That's my suggestion, yeah. Thank you. Thank you. So thank you, Martha. So let's move to the next flash presentation. This is Juan Carlos Martinez Lopez. He's from ICTP CSIC Spain, and his presentation topic is ion conducting polymers of intrinsic microporosity as selective membranes for energy storage. Okay, you are ready with the presentation?
Okay. Thank you for introducing me. I'm not going to stay for long in this slide because my colleague Marta has already explained it very well, I guess. But I'm also doing polymeric membranes, ion conductive and selective for redox flow batteries. As Paula said this morning also, membranes in the redox flow batteries are one of the most expensive parts because naphthalene is the main material used nowadays. So we are looking for more cheaper materials, and I have proposed some new polymers of intrinsic microporosity because this polymer allow us to cast films or membranes very easily in common solvents. They have a high chemical and thermal stability, and they can be ion conductors, and unless they are hydrophobic, we can chemically modify them and introduce some functional groups that help us to make them hydrophilic and also ion conductors. So we have based all of this new family of polymers in the TPBB monomer, as you can see in the middle of the slide. And we have played with different monomers and with different functional groups, as you can see, to synthesize the pinky polymer, the pinky polymer, and some copolymers also looking for other functionalities. But in this talk today, we are focusing in the pinky polymer one, in the top left one, because it has many cyano groups, and we have more possibilities to modify it. Well, to make the membranes, we follow the same technique that Marta has commented before. We use the film cast technique. We soak the polymer powder or noodles in some THF in this case, and then we put it in a glass plate and let it evaporate at room temperature until we just get the film. Well, as I commented before, we want to run the experiments of the redox flow batteries in aqueous media, so we need to make this kind of polymer hydrophilic. So we introduced by acid hydrolysis some carboxylated groups into the polymer, and we have done this modification in different times from 25 to 150 hours, and we have obtained a conversion rate between 28 to 100%. We follow this conversion by TGA and also by FTIR. As you can see in the slide, all the thermal stability of all the converted polymers are quite good, but we lose the carboxylated functional group at almost 250 degrees. But this is enough for us because the redox flow battery operate at lower temperatures. We can also follow it very easily by the conversion in the FTIR. We have done also to compare different gas absorption experiments. In B, you can see the BET surface area, and in D, you can see the Dubinin-Raduskevich surface area played in CO2. We see that when we introduce between 28 and 65% of carboxylic groups, we improve even a bit the absorption of the gases without losing any gas properties. But when we increase to 100% conversion, we lose some mesoporosity, so that's not interesting for us. And also we lose some mechanical properties. So this is very difficult for doing then the membranes and put it in the battery. So we are going to focus in the 65% conversion. Well, we have run first the test Marta explained before, just to know if some ions are passing through the membrane or not, and because we need it. So we have used a solution, feed solution of lithium chloride or potassium or sodium chloride, and in the other tank we are measuring during time the conductivity in just water. So first of all, in the top graph, you can see the different conversion ratio of polymers, and the best one, the one who performed better, is the 65% polymer, which passed the lithium 2 molar very, very fast compared to the other. So we have chosen this polymer to try with the other experiment. The first one was at different concentrations, seeing that between 2 molar and 4 molar lithium chloride doesn't make a difference. So we have chosen the 2 molar for the next experiment also. And we have tried different ions, seeing that lithium chloride passes much faster than potassium or sodium, what is very interesting. So we have a selective membrane to lithium until now. Well, we want to quantify the amount of lithium, so we have used the inline 7 lithium NMR technique. In this kind of technique, we can connect a flow cell to an NMR and follow in situ the lithium while it's passing through the membrane. So as you can see, after 24 hours, we reach a plateau, and lithium is equilibrated between the two sides of the flow cell. So that means that the membrane is like pre-treated and ready to perform in the redox flow battery. We have also done a simple experiment in the permeate tank to see if chloride is passing also together with the lithium or not, and we saw that chloride is also passing. We would like also to know if lithium is just passing through the membrane, but or also interacting with the polymer. And we saw by magic angle spin in solid state NMR that lithium is changing with the proton from the carboxylic group. So that means that lithium is interacting with the membrane. Well, as we want lithium to pass through the membrane, but not the redox species, we want to know if some common species, redox species in redox flow batteries, has crossover with this kind of membranes. So we have tested the same test in the inline NMR, but following anthraquinone and lithium ferricyanide. And as you can see in A and B, this is what should happen if this species cross past the membrane. But in C and D, you can see that the signal of the anthraquinone doesn't appear, so that means that there is no crossover of anthraquinone. And also, the lithium ferricyanide is a paramagnetic compound, so that means that if it's passing, the water signal will move, and this is not happening also. So that means that there is no crossover, but lithium is passing. So now we have a selective membrane and ion conductive. Well, finally, we have set a symmetric cell experiment using lithium, ferro, and ferricyanide. And we have tested the cyclability and also the capacity and the different current densities. And as you can see, we have tested it at 10 milliamps square centimeter, 20, and 40. And we see that we almost reached the theoretical capacity when we use at 10 milliamps per square centimeter. But when we increase the current density, we lose capacity, as is obvious. But when we recover the initial current density, we recover the capacity. And we are able also to cycle until almost 60 cycles. So that's very good news for us. This work is already published. I invite you to scan this code and read it. It's very interesting. And now we are, just to finish, we are trying to improve this membrane by using copolymers, introducing the TTSVI monomer, which is the left one. And this is a rigid a more rigid monomer, so it allows us to pass bigger ions and left more free volume in the polymer. So we have tested this time with potassium chloride because lithium passes, but potassium in the other polymer doesn't pass. In this case, it works. We have run the cell between 4 milliamps square centimeter to 20, and its cycle, the cycle stability is quite good. So we are still working on this kind of on this kind of copolymers. Well, and to sum up, just as a conclusion, we have synthesized a new family of polymers that they are conductive, they have good stability, chemical and thermal, they have a good porosity also, results, and we have modified them to make it able to pass ions in a selective way. The cyclability is quite good, and also the TPB monomer can be copolymerized to obtain new results. Also, for future work, we are now trying to use other monomers to improve these properties and play with the free volume of the polymers. The copolymerization, as I told, allow us to find different properties. And the cyano groups, we are going to try to change it to other kind of functionalities, not only the carboxylated one, but also some sulfonic group, Marta told before. And finally, we would like to improve the current densities we apply to reach higher ones. And I would like to thank you for your attention.
Thank you, Juan. It's a nice presentation. So, any questions? Yes.
Thank you. Thank you for the presentation. Nice work. Have you ever tested these membranes in full battery configuration?
No, not really. I have it writing in my notebook to do it, but we are still just playing with other copolymers, trying to improve the ionic conductivity, but I have to do it. Yeah, okay. It's a good idea.
Thank you.
Yeah, thank you.
Any more questions? Janif, expert on polymer.
Any advice?
Nice work, interesting chemical works. Yes, that is. Excuse me. Very interesting work because this chemistry is very difficult, and the chemical modifications that follows also. So my question is more related not to the chemistry that is nice, but also to the type of conductivity that you have. As you have an exchange between lithium and proton in the conductivity, you have both, I think, a protonic conductivity and lithium conducting, because the anion is fixed.
Exactly. We have only tried with lithium, but I have not tested the proton conductivity.
Yes.
But I guess we have both.
Perhaps you could, if you have NMR available, you could try to make pulse field gradient NMR and to see if you have some proton mobility.
That would be nice. Yeah, thank you.
Thank you. Any more questions? Oh, I guess thank you, Juan, for your nice presentation. So our next presentation is from Fabio Pires. So he is from University of Cologne, Germany, and he will gonna present on the topic growing hematite nanostructures under the influence of a magnetic field to boost solar water splitting performance. Okay, over to you.
So good afternoon, everybody. Thank you very much for the organizers for giving us this platform to present our work. It's an honor to be here. And today I'm talking about a little bit this project that I developed in my PhD under the supervision of Professor Sanjay Mathur in the University of Cologne. Before I go directly to the method that we use to synthesize our samples, as I'm talking, as I was introduced, I'm talking a little bit about solar water splitting. And why are we still studying this? Because when we think of green hydrogen production, the immediate and more mature solution for producing it is using electrolysis. When you use electrolysis, you have this problem that comes like, where is the electricity for electrolysis coming from? And then you can use aeolic power plants, or also you can use photovoltaic modules to support and give the electrical energy necessary for the production of the electrolysis system. And when we think about solar water splitting, we're thinking about, let's say, a technology that could be the merge of a photovoltaic system and an electrolysis system just in one technology. So if we can make it more cheaper in the next few years, it can also present itself as a good solution for green hydrogen production and decarbonization of hydrogen that is widely used for a lot of industrial processes and other applications. So in this case, we grew hematite nanostructures using a magnetic field assisting the growth of these nanocrystals. And for that, we used a typical cold wall CVD setup, but the difference of our setup is that we put a magnet into it, and then we assist the deposition with applying magnetic field. Tomorrow we will also have a presentation from Dr. Karimpur that is here from our group. He's an expert in all of this, and he will explain it way better than me. So I'm just giving this introduction to you, and then skip it to my part, where is the electrochemistry, and then I like it more. Also. So basically in this project we used iron tributoxide single source precursor to produce alpha iron oxide structures in hematite phase after annealing, doing a post-annealing treatment of this deposition for 1 hour in 550 degrees. Okay, so first thing from XRD results, we got the hematite phase, and the most interesting thing about this XRD spectra that I showed here is that we have this different growth in the 110 direction caused by the apply of the magnetic field. So for the structure that I grew without applying magnetic field, is the darker red curve, the darker red diffractogram. We can see that the growth is less than when I applied the magnetic field. And it's well known in literature that for hematite phase grown on FTO substrates, when you have this growth on 110 direction, this favors a low charge collection at the back contact, so increasing the ability of catalysis for this material. Accompanied by that, we also had this topographical change of our samples. So this could also mean that we have a magnetic, followed up by the magnetic anisotropy that we observed here in the XRD. We also have magnetic saturation in the structure caused by the application of the magnetic field. Then moving on to the application, we could see that when we apply it in a photoelectrochemical cell to do the solar water splitting, as we say, we have an increase in the photocurrents at the water oxidation thermodynamic potential for 74%, and also followed up by a slight reduction in the onset potential for starting the catalysis. Also, when we do light on and light off cycles, we can see that the material is photoactive and is not giving any performance under dark conditions. Also, from this method and this synthesis, we could achieve good reproducibility and also good stability under photoelectrochemical operations. From optical measurements, we could also see that the optical band gap that we obtained are widely reported for hematite nanostructures in literature, so it's 2.1 electron volts, which means that this material can absorb around 80% of the solar spectra, so it's a very good candidate to be applied as a photoanode for solar water splitting systems. From applying this magnetic field of 1 Tesla, we also saw that our sample could achieve higher charge separation and charge transfer efficiencies, accompanied by a really great enhancement in the photoconversion efficiency, which means that the ratio of light that is being incident into the material is being more converted into actually chemical energy in the form of hydrogen. So also a good indicative of this enhancement of these parameters is that we had increase in also the photovoltage generated by the material, which means when the material is under operation in the photoelectrochemical cell, we have a larger split of the Fermi level of the semiconductor, and then therefore we have more, let's say, energy to drive water oxidation process. Also, as a consequence of that, we can see that for the magnetic sample, magnetic field produced sample, we have lower electron lifetime. This means that this is a very good indicative that for our material has a stronger built-in electric field. As corroborating this result, we have a larger photovoltage. So when we have a large photovoltage, then charges are being separated more efficiently also, as we saw in the result above. So which means that we have a more polarized bulk. And when we have this polarized bulk influenced by the light that we are applying, we have more photo-generated charge that will promptly recombine when light is not anymore on the system. And also, we could observe an increase in the double layer capacitance of our materials, which means that also these materials, when I apply the magnetic field, I can achieve a higher electrochemically active surface area. So to sum up everything that I said, when we do this chemical vapor deposition using a magnet to change the properties of our materials, we could achieve a magnetic anisotropy with a growth, a preferential growth in the 110 direction for the hematite phase, and also a topographic change. This led to a better charge collection because of the anisotropic growth, and also increased electrochemical surface area. So producing these materials, we keep some questions for future research. Are these magnetically grown structures better templates for building heterojunctions or multi-layered materials? For example, when we're talking about solid state solar cells, we have to build a lot of layers. And if we're changing and improving these properties of interfaces, could we also change the quality of these interfaces in multi-layered materials? Also, for example, in batteries, we can also produce cathodes for batteries and with different textures, and maybe this can also help to improve the properties of the batteries. We are currently developing some works in these multi-layered materials, and this will be a topic for future discussion or discussion for coffee break if anybody's interested. So yeah, I'd like to acknowledge all of the Brazilian institutions that fund this work, and also all of the German institutions that's funding this work. And also thank Professor Mathur for his guidance throughout this project, and thank you all for your attention.
Thank you, Fabio, for this nice presentation. Any questions? Yes.
You got 110 oriented growth. Can you change it to different direction? I mean, by applying magnetic fields in different direction, or it's a tendency of the material to grow in that direction?
Yeah, for sure. We have some studies in the group in which they are changing the position of the magnetic field. In this case, I did it in the, let's say, vertical position with my substrate, but we can also change it to 90 degrees or even different angles if you want to. And these kinds of different positions of the magnetic field are proven to change also the texturization of your material. So yeah, it's possible.
Any other questions? Okay, so in that case, thank you, Fabio, for the presentation. So the next presenter is Sidone Suave. She's from UC3M, Spain, and her topic is hybrid polymeric electrodes of phosphate metal organic framework doped multi-block copolymers for fuel cells. Okay.
Thank you for the presentation. Hello, good afternoon, everyone. Yes, I am working here in the group of synthesis and processing of materials from this university. And today I'm going to present a brief work of hybrid polymeric electrolytes of phosphonate and multi-block copolymers for fuel cells and also for electrolyzers. Okay, nowadays we have a challenge that is the decarbonization for a sustainable energy future. So I'm going to present two types of devices that could help us to reach this goal. First of all, the proton exchange membrane fuel cells. This device uses hydrogen and oxygen to produce clean energy. This device is highly efficient. There is no greenhouse gases production, and this clean energy could be applied on transportation or power generation. On the other hand, the proton exchange membrane water electrolyzers are devices that by the split of the water by electrochemical process, we could obtain green hydrogen. This green hydrogen could be stored as a carbon-free fuel. As you can see, in general, this device has a cathode, anode, and a polymeric electrolyte in the middle. Which are the requirements of this electrolyte? Basically, the first one is that this electrolyte has to avoid the electronic contact between the anode and the cathode. Also, it has to promote it must have high proton conductivity, dimensional stability, moderate water uptake, and chemical and electrochemical stability. Nowadays, as you know, and it was presented before, the material used now is Nafion. This is a type of material. There are different types of materials produced by DuPont. In this case, Nafion has a limitation, as we said before, that is the fluorinated present. The presence of fluorinated substance on the structure, which are being limited by the European Commission. Okay, so we have to look for alternatives for this material. In this case, we are going to propose a hybrid membrane that could enrich these properties. We are going to use a copolymer, like the polymeric matrix, and we are going to use a low charge of MOF in order to improve the properties. In our research group, we have been developed these copolymers called SPs in different ratios. We are using a multi-block that has the block of polysulfone and the other block of polyphenyl sulfone. And after the sulfonation reaction, we are having a polymer that has proton conductivity. Okay, we are the advantage of this material that we have no fluorine in the structure. For example, in the 50-50 copolymer, we have this characteristic of this material that we can see that the water uptake is under 30%. The mechanical properties are measured in a DMA device in a tensile mode. We reach the tensile strength over 80 megapascal. The thermal stability determined by TGA and DSC, it could reach a maximum of 100 Celsius. And the ionic conductivity is very high. We measure by impedance spectroscopy in situ, that we mean inside of the fuel cell, and in ex situ in a homemade cell here in the university. We also already test these type of membranes in a fuel cell test, and we can see that this material can reach around 400 milliwatts centimeter square in these conditions. In this case, we are going to choose a MOF. This MOF is IF7, which is a collaboration with our group with Indea Energy. They developed it by first time, and we can see this structure has the metal is bismuth, and the organic linker is phosphonate. This structure can let us allow or carry water molecules in the inside, so it can help to improve or increase the water uptake of the membrane. And also it has a ionic conductivity itself. Okay, so finally we have a hybrid membrane that has the polymeric structure, which is going to give us the mechanical stability and the ionic conductivity. And on the other hand, we are going to use the IF7 MOF that also can improve the water uptake and the ionic conductivity of the hybrid membrane. Finally, we prepare the membranes by casting. We prepare the pristine membrane and 2 and 5% of the of IF7. As we can see from the microscope image, we got a homogeneous distribution of the particles in all the membranes. And in terms of properties, we got to increase the water uptake to 40% of the water uptake for the 2 and 5% of IF7. And in terms of mechanical properties, they remain stable. Okay, we have no decrease of mechanical properties. In terms of ionic conductivity, this is the ex situ cell that I was mentioned before. We got that the membrane with 2% of IF7 increased the ionic conductivity at higher temperatures. So we move on with this membrane, and we tested on the fuel cell. This fuel cell test system is in the ICTP Institute in Madrid. This is part of a collaboration with Carmen del Rio, where we used to test all the membranes. And here I show the polarization curve of the membranes, 0% and 2%, and you can see that the membrane without MOF exhibit 320 milliwatt centimeter square, the maximum power density in the cell, and then the hybrid membrane reached to 450 milliwatt centimeter square, which is an improvement in terms of power density and performance in the fuel cell. And actually, we are getting closer to the Nafion 112 in similar conditions. Okay. Also, I'm going to move to the electrolyzer. This is a lab scale electrolyzer designed by H2 Green Company, which is a Spanish company. They designed this electrolyzer for us. For test the membranes, here we can go into a current density maximum of 1,000 milliamp per centimeter square, and the temperature range between 25 and 65 Celsius. Here is where we place the membrane, the proton exchange membranes, and we are going to see the results of the polarization curve of the 2%, the hybrid membrane with 2% of IF7. We can see that at the higher temperature, and given a maximum value of voltage of 2.2, that at the higher temperature we got 290 milliamp per centimeter square, which are values, very promising values compared to Nafion, okay, Nafion 115. And actually, this is a Nafion, Teflon reinforced Nafion that is actually sold only for electrolyzers, and we reach the same current density in the same device. And basically, as conclusion, we go to prepare hybrid membranes, and we test them on both devices, and with the results, we can say it's promising to use this polymeric electrolytes for dual performance in the devices. And the knowledge of these results are part of the project H2 Mod with our university and in their energy. And thank you. If you have any question.
Thank you, Sidona.
Thank you, Sidona, for your nice presentation. So, any questions in the audience? Anyone? Okay, so in that case, I'm not expert on that. Anyway, so thank you again. So the next presentation is from Natalia, and she's from Universidad CU San Pablo, Spain, and her topic is about CS2 Ti5O11 y sus derivados como electrodo negativo, ¿sí? Para baterías de ion litio. So sorry for my Spanish.
Sorry, can you help me with?
Yeah, which one?
I connect my computer, but it's not working.
So I mean,
I asked before and they said that we can use this, but no. I can't use it in this computer from my university. ¿Tú antes has usado el HDMI?
Por ahí.
Sí, se ha conectado el HDMI, pero no.
¿Y ahora qué pasa? Que
No,
no sale
no hace
tu
nada.
pantalla.
No sé cómo lo habéis hecho.
Es que ha sido un chico que se ha encargado aquí. He visto que hacía la conexión y no sé más. No veo que sí está. Es que debe haber
so you can't use pen drive here.
I can send by email. Es que no me dejan meter pendrive, o sea, está bloqueado el puerto. Sí.
You can send a mail to me.
Yeah,
I will delete after that. No, it's okay. No problem. We have time. Nacho can see if it's connected to this. You have in your mobile?
Una pantalla compartida. No se puede poner la aplicación, o sea, tiene que ser la pantalla replicada. No puedes. ¿Quieres tu propio ordenador?
Sí, puedo. Si no, lo mando por correo. Okay, sorry. I'm going to present, I am a PhD student, and I'm going to show you a part of my study in CEU San Pablo University. And the title in English is Pentatitanate of Cesium and its derivatives as a negative electrode for lithium-ion batteries. Some people have explained how a battery works, so now I'm going to go to my goal. We have two main objectives in this part. One of these is to do the synthesis and optimization of different titanates, which are pentatitanate of cesium and its derivatives of lithium and hydrogen. And the second objective is the electrochemical characterization in lithium versus lithium incandescent. Sorry. Firstly, we prepare cesium pentatitanate from titanium dioxide and cesium nitrate in ceramic at 1000 degrees in an oven. Using X-ray diffractogram, we can check that we have the product that we need. By SEM, we can check that the length is between 1 and 10 microns long. And as we have the product that we need, we have checked the electrochemistry doing a galvanostatic cyclability test. And we see that the capacity, the specific capacity is not good. It's around 20 milliampere hour gram. So this is not a good result for batteries. With this result, we have prepared the lithium derivatives from the cesium sample with nitrate of lithium in aqueous solution around 10 days at 60 degrees. We obtain the first derivatives. With X-ray diffraction, we can check that the peaks have changed, so we have a new sample that can index with the cell parameters that we have in the bibliography. The morphology is the same that in the previous sample. We have needle-like morphology, and we can check from EDSM that the residual cesium is around 0.6%, so it's almost every cesium change. We test a cyclogalvanostatic test, and we can see that the specific capacity has increased a lot from 20 to 100 milliampere hour gram. And the second derivative is prepared from the previous titanate in acid solution, in this case with hydrochloric acid, during 9 days at room temperature. And we can obtain the hydrogen derivatives. If we do the X-ray at the freshly sample, we can see that we have the system with 3 molecules of water. But if we dry in an oven at 70, 80 degrees, we have the sample with only 1 molecule water. As we have to prepare electrodes and dry it before doing a coin cell, we choose the sample with only 1 water. To check this evolution, we want to know if the loss of water is from 3 to 2 ending up in 1 water. So we did X-ray thermodiffraction, and we can check that we have 3 molecules of water until 70 degrees, and after that we have 1 molecule of water pattern, and at 200 degrees we lose our extractor and we only have titanium dioxide. The morphology is maintain the first one, and the residual cesium is around 0.6%. So we do the same test for cyclability, and the specific capacity increase. This time is around 150 milliampere hour gram. So this is a good result for lithium-ion batteries. So we did an experiment at different C rate. At high rate 2C, we can see that the capacity is not bad, it's around 50, and that if we come back to C20, we recover the first capacity. So conclusion, if we compare the 3 systems, we can see that we have increased the capacity changing the metal. So we are going to work with this material, the hydrogen one, because it's interesting and it's the best one. So thank you everybody for your attention.
Thank you.
Thank you, Natalie. It's a nice presentation. Any question from the audience? Yes.
Why the reaction time is so long?
Because if we did less days, the residual cesium is higher. So we are doing ion exchange. If we only do 1 day, we have 3% of residual cesium.
That's precisely my question. This ion exchange will work with all rare earth elements? Instead of cesium, suppose I have lanthanum or some other elements. So is it only it works with cesium, or for any other rare earth it will work, you think?
We have thought about potassium, but as we are working with lithium-ion batteries, this is the best ion exchange that we have.
Any more questions? Anyone? I have one question.
Sorry.
So you have shown the capacity graph and everything, but I didn't see any charge discharge graphs where I can comment, because after the first cycle there is almost 50% drop, I guess.
Yeah, we lose capacity from the first
but
cycle.
I want to see the charge discharge graphs, like how, like.
I have it, but like it's a class I don't have here.
That is my suggestion. If you put it, maybe I can see. And anyway, that's my only suggestion. Okay, thank you. So our last presenter is Zachary Warren. I think I pronounced right. He's from Instituto de Cerámica y Vidrio, CSIS,
ICV,
Spain.
yeah.
So his topic is about investigating soluble intermediates of LPS during liquid synthesis of solid sulfide electrolytes. I guess you are ready, right? Okay, over to you.
Thank you. And thank you for the introduction. Since I'm the last, I'll try to make this as entertaining and informative as possible. So my name is Zach. I'm with the Institute of Ceramic and Glass, so Instituto de Cerámica y Vidrio. We're part of the CSIC. And this investigation is mainly about how we can synthesize solid materials for solid-state batteries. In this case, sulfide materials. What we see in the battery market today is an exponential growth in demand for lithium-ion batteries. These types of batteries are in almost everything. Portable electronics, electric vehicles, we see them in trains, and even now in airplanes. The problem is we also see an increase in incidences of fires and thermal runaways with these types of batteries. When you have a really, really high energy capacity battery that's in contact with a volatile or flammable solvent and there's an accident or some sort of malfunction with the battery, of course, we can result in something extremely dangerous. And I wanted to include this. I'm sorry I wrote this in Spanish, but this is from the New York Fire Department, and this is from last year. They put this notice out that the #1 cause in fires in the city of New York and fire-related deaths was due to lithium-ion batteries. It's because of this is the primary reason. I always present this with all of my presentations, is because this is the most important aspect to me. If we're going to synthesize materials or batteries that are going to be very, very high capacity and have very high energy, they need to be safe. We have to do it safely, and they have to be safe to use. So safety is #1. If we can synthesize materials for batteries and inorganics that are completely inorganic, we can essentially render these batteries inflammable or have very, very low potential for thermal runaway. Secondly, we study solid-state batteries using sulfides because of the types of ionic conductivities that these can offer up in the range of liquid electrolytes. And these also present really, really good mechanical properties because these are glass-type materials. And lastly, I included economic means because I am a synthetic chemist, and so I study how we can synthesize these rapidly and efficiently. And so since we're on the topic of synthesis, a common synthesis technique for these types of materials, for electrolytes, is solid-state synthesis. These could be mechanical ball milling, melt quenching, spark plasma sintering. And these are very beneficial because these can render really high yield products. These have really, really good mechanical properties and really high ionic conductivity. The caveats are these are extremely energy intensive processes normally, especially for these types of materials. These synthetic processes generally take days to prepare or extremely high temperatures. And so what we do at the Institute is we study how can we synthesize these using solvents, solvent-mediated processes. And these are kind of interesting because this is not, in reality, this is not a liquid phase synthesis. This is a solid phase synthesis that is mediated by solvents. So what we essentially do is we take our precursor materials. In this case, this is LPS system, that's lithium phosphorus sulfide. So we'll take lithium sulfide and phosphorus pentasulfide, and we react them in some type of solvent that we've selected based on whatever type of conditions that we're looking for a type of electrolyte. We react it we can do this in 30 minutes or less with microwave irradiation. We can use ultrasonication or just mechanical stirring. Low temperature, usually about 30 degrees, and then we remove the solvent and then we perform an annealing step. This annealing step is critical for these types of materials as these form complex solvent formations. This is really not well understood. These types of syntheses are fairly new to the field. The first one reported was only 10 years ago, and there's been very, very slow progress on understanding how these reactions work. But one thing that's really interesting to take away is whenever we perform this reaction in any type of polar solvent, aprotic solvent, we always see this beta phase, which this is interesting because we're synthesizing this at low temperature at 30 degrees, when normally this is only seen at 700 degrees through solid state synthesis. So this is a way we can essentially synthesize materials using much less energy and much, much faster for commercial purposes. Now, we don't really understand the facilitation between these solvents and these precursor chemicals that make these electrolytes. And so what we're focusing on, like many people have spoken today, are in operando or in situ measurements and techniques. Of course, we're not studying batteries, we're studying materials or syntheses on how we make materials for batteries. And so we started using Raman spectroscopy, in situ Raman spectroscopy, using microwave radiation. This is fantastic because these types of microwave reactors are isochoric, isothermal. And so whenever we measure these, if we can identify the signals that are coming off of these thiophosphate systems, we can actually extract thermodynamic information and kinetic information from these reactions. And so this is kind of just a basic diagram of what it looks like if we hit it with a Raman laser. And this is the overall reaction start to finish, what we see, and just some integration. These have never been reported before. There's no reports on kinetics or thermodynamics from these types of reactions, because they are solid particles that are reacting to make something soluble, and then they solidify into a particle. So we're going through 3 phase changes for this to happen. So these are incredibly difficult, but this is an opportunity for us to learn new techniques and develop new techniques. And another one that's interesting, someone was speaking about time-resolved X-ray D. This is a new technique that's been developed over the past few years, which we can do high-energy X-ray D liquidography, and we can measure the phase change, which hopefully in this next coming year, we will. I'm going to leave you all with that. I don't want to get too much into it. We did just put out a paper about this on how we can actually synthesize these very, very rapidly using solvents, if y'all want to read more about it. And with that, I will leave you. Thank you all very much for your attention.
Thank you. Thank you for a nice presentation and nice talk about solid-state batteries, solid-state electrolytes. So, any questions? Yes.
I have a question related both to the hygroscopy of your material, and the second part is about the mechanical strengths that you can get for your for your glassy electrolyte?
Yeah, so these materials are extremely sensitive to humidity. So these are extremely hygroscopic and they're very reactive. Lithium sulfide breaks down in the presence of moisture and it'll create hydrogen sulfide gas. So these are all performed in argon-rich environments and very, very dry solvents. So we have to take a lot of care to make sure not only are the precursors dried, but the solvents are dried before we perform these. Yeah.
Thank you. And did you think that in case of a dramatic event or something, you could produce with sulfur compound hydrogen sulfide?
Absolutely. That's also something that's being studied with these types of batteries. So sulfide solid-state batteries are very popular right now for being studied. But one of the problems is, depending on the type of electrolyte, that's the bulk material of the battery that we're using, if it's LPSC, so it includes some sort of halogen, or if it's LPS, which is a glass system, there's two different mechanisms that are known for types of thermal runaway. One of them produces hydrogen sulfide gas in the battery. So that's another safety aspect that has to be, we have to overcome that for these batteries to be viable in the future. So maybe they're not flammable, but they're extremely toxic if they break. So.
Yes. What is encouraging? Yeah, no, I get it. We have I did about 30 years ago a survey for France CNRS about the material, the future of material for battery, and I met the people from Everready, Energizer.
Oh,
and
yeah.
they say we have a small cell with a glassy sulfide, and this work more than 10,000 cycles, but we are not able to make battery
incredibly difficult. We manufacture micro batteries in our lab. Yeah.
No thing, huh? So I think it's something very attractive, but it's very challenging.
Yeah, some of the largest companies in the world are trying. Samsung is working on this. Toyota is working. CATL is working on this. This is a big focus right now, is to push solid-state batteries because of the high energy density that they have, not inflammability that they have. So essentially, if you have a full all-solid-state inorganic battery, you can double the range of an electric vehicle with the same mass. So they're very attractive, but they all have obstacles. So.
And what do you think about the blending of this with some kind of polymeric material? Do you think that it's a future or not?
I think it can be, based on the premises of moving towards a solid inorganic battery. I think we're kind of shoot ourselves in the foot there, but polymers are very attractive right now too, based on conductivity and their performance that we see on them. So a blend between a hybrid inorganic and polymer batteries is really ideal. And for thin films, for cylindrical type batteries, most thin films are made from some type of polymer, so that we see for solid state batteries. So, yeah, it's not, in my opinion, I don't see sulfide solid state batteries necessarily the direct future, but it's going to be a blend of something. Yeah.
Yes, thank you.
Yeah, thank you.
Anyone? Yeah.
Thank you for the entire presentation. My question is about this kind of synthesis, in liquid synthesis. One of the ideas is infiltrate a cathode or a system. This electrolyte.
Yes.
How is the reactivity of this?
Yes and no. So this is, what we have here is simply just the synthesis of a solid state electrolyte, and that's it. However, liquid phase processes are used for infiltration of cathodes as well. So if you have some type of rigid carbon structure, we've seen sulfide infiltration using liquid phase processes as well, because it makes lithium sulfide and polysulfides extremely soluble and able to infiltrate these processes, or the cathodes, or whatever anode cathode you're studying. So yes, there's a lot of applications for it. These, however, these are extremely reactive. So in the case of polysulfides, you're looking at, is your question more about if you use polysulfides in like a hybrid battery, or like infiltration of the cathode during the cycling and
infiltration of the structure of a cathode with some porosity?
Yeah, there's some papers that came out of Columbia just about that, using exactly what I just spoke about, is using some type of structure and infiltration process using liquids for polysulfides, but we don't really study that. We study how we synthesize the materials and to just make the batteries. Yeah.
Another question is, you produce a powder
Yes.
And then you need more processing to get
No.
solid electrolyte.
It depends on the type of material, and it depends on what it will be used for in aspect of the battery. For cathode synthesis, we would primarily, you want something really low electrical conductivity, or really high electric conductivity and high ionic conductivity. But for a separator, you want really low electrical conductivity and high ionic conductivity. So if we take, for example, this material, and then we anneal it at a high temperature, we'll get something that's really, really crystalline. And these crystalline materials that we see, like with LPSC, that have halogen, so it's an LPS system that has any type of halogen, whether it be bromine or chlorine or iodine, generally have really, really low electrical conductivity after we anneal them. So they do need additional processing in that fact. So sometimes you do, and sometimes you don't, depending on the application of the electrolyte, whether it's catholyte, analyte, or separator. Yeah, thank you.
Okay, any other questions? Anyone? Oh, I have a small question. Like you're talking about mechanical properties and conductivities. So you have anything like in comparison studies, like somebody prepared in those materials, the electrolytes in solid state method and your method also, and have a like
So
hardness test or something.
When
like
we look at,
to make
yes,
superior.
actually I have a paper coming out in 2 weeks about that exact question. So one of the caveats to liquid phase processing is a benefit is we synthesize them very quickly. You know, we can cut 3 days of synthesis time to less than 6 hours and using minimal temperature, which is fantastic. However, we also cut the ionic conductivity significantly. These materials, through mechanical ball milling, normally we see they're glass. And so they really have, glassy materials are known to have really good mechanical properties as well as having high ionic conductivities. But when you go to a more crystalline substance through these, for some reason, we see a reduce in ionic conductivity, usually about 50%. Now they're still in the range to where we would consider them ionic superconductors. So we're still over 5 millisiemens for these types of materials, but it's a lot less than 12 millisiemens, which we could see through a mechanical process. So this is more of an approach of how can we synthesize these for commercial means. Mechanical ball milling for these, normally, if this was an oxide type material, no problem. But these are so sensitive to moisture and air that these all have to be done in some type of controlled environment. And so mechanical ball milling is not really feasible. And normally the batches that we see, even coming from Toyota and Samsung, are still the largest, are 0.5 kilogram batch. Well, for an electric vehicle, I mean, you need 50 kilograms or more, you know, for one battery. So that's just not reasonable.
Okay, another question is that like you work on this sulfide means
yes.
type of thing. Suppose Lisicon or some other solid state electrolytes people are working. So in that cases also somebody can research and do this kind of methods like what you have proposed, and then in that method they can get that kind of results, and then we totally cut off the solid state methods.
I would say yes to that. I would love to say yes to that because that would mean I've won at chemistry. But it works for some types of electrolytes, but not all. So we're starting to see oxyhalide electrolytes coming out now, which are even higher. They have better properties than sulfides, but they're extremely difficult to synthesize. We've tried it with solution processes. We cannot get them to work. Oxides, they're almost impossible to do with this. Sulfides are ideal because for some reason with moderately polar aprotic solvents, they seem to facilitate reactions ideally. Yeah, I wish it were true.
Yeah. So any other questions? So in that case, thank you so much.
Thank you
it
very
was
much.
a really good presentation. So I guess we are finishing in time actually. So that concludes the day one. So hopefully you all get fruitful sessions and you have enjoyed the day one. So we'll resume tomorrow as a day two, and we'll have some exciting presentations and sessions also tomorrow. So see you all at 9:30. So till then, have a nice day. Okay.
que se habla de la